John.
All right, everyone, welcome back to the channel. Those of you, I believe, will remember the last edition we did of this with Matt LaCroix and John F. White. Now, back with us today, of course, Flat Earth Dave, Dr. Matthew Yelovich, and Angels of Light. We are going to be discussing some stuff that we didn't get to dig into last time. And of course, we brought people from various fields to discuss this topic today. So what I want to do is to get straight into it. Flat Earth Dave, if you could sum up in some shape or form, and I know that's a tough ask, the position that you've decided to kind of devote yourself to.
You know, I'm gonna switch it over to Angel because he just said it before we started recording. He's got the position oiled down to basically 3 sentences. Go ahead.
All right. Well, yeah, our position is that we live on a level topographical plane. It's stationary. We're in an enclosed system. We have luminaries above us. We are geocentric, and all the luminaries rotate clockwise around Polaris, east to west.
Okay. So, Dave, nothing to add to that?
No, it's perfect.
All right. Matt, you've been on the channel before. I think so. Many people here will be familiar with you. Maybe you just want to throw us a very small introduction to the very least, and then kind of give us an idea of what you think about that model.
Well, it's good to be back, Will. Sure, I'll give a little introduction. I'm a professor of physics, fluid mechanics, and thermodynamics. I've been doing it for about 20 years now. So I have a pretty decent background in those areas. Hopefully it will be able to contribute somewhat to today's conversation. I'm a professional engineer. Prior to my work in academia, I worked in engineering for several decades. And here I am. So I just want to have a great discussion today. I want to hear the positions of both Dave and Angel, and maybe we could have a respectful discussion.
Awesome.
Starting right from there, obviously this model that Angel is presenting is a new one and will be a new one to a whole lot of people. And correct me if I'm wrong, and this is why you're here. Excuse me. This is why we wanted to have this discussion. These models and this model that he's presenting and the heliocentric model both cannot be correct. If I'm to understand this properly. Could you maybe help me make sense of why that is and how we can, how I'm supposed to make sense of a flat shaped model versus the one that we're obviously taught in school?
Yeah, you know, we have a model, if you will, but we realize that there's a lot that we don't understand. The globe doesn't have a model at all. The globe is the globe model, if you will, defies natural law. It has air uncontained next to a space vacuum. It has gravity, which is unproven, which defy electrostatics, which is proven, which is 10 to the 36 power stronger. We can go through all the different points and show you how, yeah, one of them is totally wrong, and one of them, we're certainly figuring it out. But we'll go over each one of those things, and then let the listener come to their own conclusion. One thing I always say is don't believe anything that Angel and I say. Don't believe anything. Verify everything. We're gonna show you stuff that you never thought of. We're gonna show you stuff that you were programmed not to believe. And you know, belief is the enemy of knowing. For example, Matthew, test question: where do I live? We talked about it before the show. You can look down. You wrote it down.
Yeah, Connecticut.
Connecticut. Now, do you believe it or do you know it?
Well, I trust that you told me.
So you believe it?
Yes.
You believe it. So you heard me say it. You're like, why would he lie? He sounds like he's from Connecticut. He's got a little bit of a New York accent. That's near, you know, you stored that as truthful information, but you don't know it. You believe it. So we believe a lot of things that we've been told all of our life. But to know them, you know, I spoke to a principal and two science teachers the other day, and I said, what's your number one proof you live on a globe? And they're like, well, I never really thought about it. You know, they just believe it because that's what they were told. So I'll toss it back to either one of you guys. Where you want to go?
I guess we can start off with the first thing that Angel said, that we live on a, I believe you said level topographic plane. Is that correct?
Yep.
Okay, that's a good start. So let's define that. So are you saying that the Earth as we know it is not a sphere, correct? And that it is perfectly or relatively perfectly flat for all of its expanse. Is that correct?
Level and horizontal.
Yeah, level horizontal and has topography.
Okay, fair enough. So how long, okay, if that's the case, let's just for the sake of argument say that that's the case, that it's level, flat, horizontal, whatever you want to call it. How far does it extend?
Okay, well, that's the thing. Our known region, it would be Antarctica that we're allowed to go to independently. So past the 60th South parallel, there's actually an Antarctic treaty, and you have to get permission to be able to go further than the 60th parallel, which would be encircling the whole Earth.
Okay, I see the picture there. Okay, so you're saying that Antarctica is the outer border? Would that be the correct way to say it? The outer border of this known Earth?
Yes.
Okay.
Well, let me just chime in there. Antarctica is the shoreline that contains our water. Large bodies of water need containment. Now, does Antarctica, where we think Antarctica is, does it go all the way around or does it go farther beyond it? We don't know because we don't have access. We can speculate, we can make claims, we can show evidence. But we don't know because we talked about the Antarctic Treaty. You have all of these islands out here. If everyone remembers the Falkland War for the little island, why are they fighting over that? These are where military bases run by the Crown are there, and they guard Antarctica. They don't allow anybody unsupervised, without prior permission to go beyond that 60 degrees south location. So there it is.
But people do go to Antarctica.
Absolutely.
Okay. So they've acquired permission to go there.
Yeah, but there's no free and independent exploration of the outer south.
Okay. All right. I am somewhat familiar with the Antarctic Treaty. It was signed by even the Soviet Union back, I believe, the Soviet Union and the United States, they all agreed on that treaty back in the 50s or the 60s?
Late 50s, right?
Okay. Okay, so let's go back to the whole flat plane. Now, the obvious arguments against that would be that, the typical arguments we hear or even see is that as a boat moves out into the distance, you can see it the further out it goes past the horizon, which could be calculated. To calculate the distance of the horizon is probably not a big deal, but you could see that parts of the boat start to disappear, and then eventually the boat disappears over the horizon. Presumably, this would be going around the curve of the Earth, and that's why we can't see it. So that would be an obvious argument, a counter argument to the whole flat plane.
Sure. This is one of our.
Okay.
Let's. I mean, if you're done with that point, I don't want to go to another point.
It's just a good starting point. We can discuss that. I'd like to hear how you would argue that.
You agree you can't see my mouth right now, right?
No, I cannot.
Because it's behind a physical curve, a physical obstruction.
Yes.
So the globe has a required physical obstruction at a certain distance. And do you know what the curvature formula is by chance?
I could calculate it myself, but is the radius of the Earth? What is the radius of the Earth? I wrote it down.
3959.
30. What is that? Miles? I work in kilometers.
Yeah, miles.
Okay, I have 6,300. Okay, so what was that again in miles?
3959.
3959 radius. Okay. So you're asking me to calculate how much disappears over the horizon.
Right. So you don't need to calculate it now.
Okay.
We know it. We're going to tell it to you. Don't believe it. Verify it later so we don't waste.
I have a calculator here. Go ahead.
So at 3 miles, the curvature is 6 feet. At 10 miles, it's 66 feet. Now, if we had a perfectly glass calm water day, cool, clear, no humidity, no pollution, so we have the best visibility, the farthest that horizon should be to a 6-foot observer is 3 miles away. Anything past that will start to get hidden behind a physical curve. Can you agree with that?
I think those numbers are correct. I just checked. There is an Earth curve calculator.
Yeah. So we have them. Verify them later, of course.
Yes, that sounds correct.
And if I sat down, I'm now no longer 6 feet tall. That horizon's going to come even closer to me because I'm lower.
Correct. Your perspective is different. Yeah.
So we're going to show you some observations that that require magical refraction. So out here, there's no boat. You can't see a boat. So look carefully. Ready? So as we zoom in, we're increasing the angular size. So we're making our aperture bigger and bigger and bigger. And as we do, all of a sudden you see, oh, look, there is a boat there. Now my finger can't hide that whole boat. But if my finger was a wave in the foreground, as I zoom out, my finger is going to hide the whole boat. Okay? And these little waves in the foreground, the boat looks like it's going over the curvature. But you can agree that that boat's not going over curvature. It's going out of our ability to see it. It's going out of our angular resolution limits.
Yes, I agree. Yes.
If it was behind a physical curve, we couldn't zoom in on it. No, even if we had the Hubble telescope.
Well, there are other elements at play here, such as the refraction, but yes, I would agree that. How far is that boat away? Is that?
We don't know. We don't know on that one, but we do have other ones where, Angel, are you able to share images well, or I can share them and you can talk about them?
Yeah, I mean, I can show my own observation that I did. I've got the video ready. I can share it.
Yeah, some numbers would be good. If we could know how far away that particular object is, then we could calculate whether we can actually see it, then accounting for refraction.
Let Angel show you this demonstration, then I'll show you something that we know the exact numbers and you can verify.
Okay, great.
So just very quickly, right? You're saying that this horizon is curving down and away from us in all directions, correct?
Well, that's the model that we use in physics, correct?
Okay, so watch this. So it's going to reveal a buoy and a boat that wasn't previously visible, see? Now, my second question to you is, you just said that it's curving down and away from us in all directions. Now, my next question would have to be then, if that's the case, then how come when we zoom in onto the horizon, the boat in the distance appears higher in elevation than the buoy? If it's curving down and away, the opposite should be true. The boat should appear lower than the buoy. If you zoom all the way in on curvature that's curving down and away, it should curve more down and away from you as you zoom in.
No, do you know the distance of the boat there? I mean, the buoy.
I know my altitude above the water there was 6 feet.
All right, so you're at 6 feet, yeah. And how far away is the boat in miles?
We don't know the exact distance, but the point he's making here is the more distant object appears higher than the closer object. But when we're on a ball, we're always on the top of the ball, and the farther things get, the lower they should be. They go down and away. When you go across a ball, everything goes down and away.
Yes. I guess my question is, if we could have some numbers here. I know what's happening. I know what's happening here because the human eye can only see so far, and you were using obviously some form of camera. You were zooming in. Now it's easy to calculate how far that horizon line should be. You said you were at 6 feet. At 6 feet, the horizon should be about 3 miles away. So that horizon was 3 miles away from your perspective, from where you were standing. So that buoy was closer than that. That's why we can see it, right? Correct.
Yeah. No, well, we could see it. We could see it when I zoomed in. Yeah.
Yes, and again, human beings can only see so far. You know, if you are looking at a car or something, and you walk on a perfectly flat plane, and you walk further and further and further away from it, that car would eventually disappear. It would kind of merge into the horizon. It's perspective, right? So I guess the best way for the only way I can really analyze this is to know the distances, because if you show me something that I should not be able to see, then that would be a point well made. But right now, I don't know the distances.
I'm going to show you 2 points. Now, these are oil rigs, and we know exactly how far they are because they don't move, right? And the camera is 1 foot off the water here. Now, again, you need to verify this. I could be lying. It could be 100 feet in the air, right? So it's 1 foot off the water. This one is 6.2 miles away. Doesn't seem like far, 9.4 miles away. But according to the Earth Curve Calculator, this platform should be hidden by 59 feet of curvature from that elevation. Not only can we see all of the water leading up to it, we can see the horizon far behind it. We can see the horizon far behind it. Let me show you another video of this. So this horizon is far beyond the platforms.
Okay.
So right here, the water would need to be refracting up almost 60 feet. Out here, it has to refract up maybe hundreds of feet for us to be able to see it. But the horizon is far miles beyond the horizon, beyond the platform, which would be impossible on a ball.
Okay, so you're saying that the camera that took that picture was 1 foot off the water?
Correct.
So the first one was 1, this one's 8 foot, and I can actually show you the video of that confirming it, but yeah.
Oh, okay, so let's go with the 8 feet then. That's easy. These are easy calculations. So 8 feet, and you're saying that that platform is 9.4 miles away?
The one in the back on that image now is 10.1 miles away from 8 foot.
Okay, what's the one in the front? Because I can see that better.
About six.
Well, it doesn't matter because the horizon is far beyond the second one. The horizon, how can we see the water beyond it? The horizon should be in front of it.
Well, the horizon at that distance, at that height, so if you're 8 feet above, the horizon should be about 3.5 miles away.
Correct.
Yeah, there's an inconsistency there because the horizon, if that platform is, as you say, 6 miles away, then I can clearly see the horizon behind the rig. And that horizon in the background should be, like I said, 3.5, let's say 3.5 miles away, but it's obviously well beyond.
Something for you to look into. Something for you to look into and confirm.
Now, again, these are pictures that you're showing me, but let's just, for the sake of argument and, to have a good discussion, let's just assume all the numbers are correct. Then that is inconsistent with the Earth curve calculation. However, we have to factor in refraction, but refraction is only about, at most, it could only reduce curvature probably by about 7 to 10% at most. So it wouldn't.
Could I get in here about refraction? Yep. Now, the law of refraction is Snell's law, which actually requires 2 different isotropic mediums. Now, number one, if you're going to invoke a density gradient, corpuscular rays go through the density gradient and they do not curve. Now, second of all, when we're looking horizontally over the Earth, there's no density gradient. Okay, because we're looking horizontally. The density gradient is vertical. So you can't really even invoke refraction on the Earth, to be honest.
Unless the Earth is curved.
When you say density gradient...
No, you can't. You're right, because it would be the same density. You're right.
When you say density gradient, you mean the change of density of the air from the surface all the way up.
Yep.
Yeah, if we calculate how much refraction there would be from the top of Mount Everest to sea level, it's 0.0%. It's negligible.
No, refraction. You're right that refraction is not a big factor. Like I said, at most, it would probably be in the range of a few percent, maybe 7%. It wouldn't account for that much of it wouldn't cause that much more to be visible over the curve of the Earth. So I don't think refraction is a huge player. It is a minor player. We can argue, how much, but based on that rig that you showed me, something doesn't seem right there. Assuming the numbers are correct, I'm taking your word for it.
Club Libertas, the elite private membership club for the modern mystic, exploring powerful teachings on spirituality, self-awareness, ancient wisdom, a deep dive into meditation, mindfulness, and transformational practices designed for those ready to lead their own journey. Are you ready to step up?
Matthew, let me just a side note here. I'm going to share a playlist with you after the show or whenever, and listeners, you can post it. It's a list of experiments that were already done where we show we document everything. That way you can watch those and then reproduce any ones you want. But we've done all the work for you because these experiments, you got to go out there. The conditions have to be right. If it's wavy, there's an issue. If there's fog, right? So So all of these have been done. We have dozens and dozens and dozens of videos for you to watch. But here's another one that we had a guy do on a lake. So large bodies of water at rest lie flat. When they get cold, they freeze flat. So here's a canal or a lake. We got a camera 6 inches off the ice. And in the video, you can see that he dug down, shows you where the ice is. So we're not on top of any snow or anything. And then he put these lights at 8 miles, 7 miles, 6 miles, and 5 miles. Now, that doesn't seem far. But at 6 miles away, the horizon should be 0.88 miles away, less than a mile away. That's the Earth curve calculator, and we're looking on ice.
Sorry, at 8 miles, is that right on the surface of the water?
It's right on the ice.
Oh, I see.
And I think these are 6 inches off the ice, right? But again, you have to watch the video. But again, 6 inches a foot isn't going to make a difference. Watch. At 8 miles, including an absurd amount of refraction, 30 feet, 22 feet, 15, and 9 feet behind the curve of the Earth. Remember? You can't see my mouth because it's behind the curve of the Earth.
Yes.
Okay? So if we look at it, we have two options. We got the camera on the ice, and it's looking at all of these things across the level ice. That's option number one. Option number two is the camera 6 inches off the ice at 0.88 miles away is the tangent of the Earth. It's skimming across the tangent, and all of these at nighttime with no humidity are refracting up and stopping exactly at that tangent line. None of them are going above. None of them are going below. They're just magically stopping at that tangent line. Option A, flat Earth. Option B, heliocentric religion.
Yeah, the only way to be able to see those multicolored lights would be to invoke refraction.
Or flat Earth.
Well, yes. I mean, again, there's two options here. So there's the absolute flat Earth, and that way you should be able to see them, assuming there's no density, obscuring, like the further you see. That's why we can't see Mount Everest from, eventually.
That's not why. Oh no, you can't because of the density. You're right.
Correct,
You're absolutely right.
So assuming the density is not an issue, it's a very low humidity day, then the only way to see those lights are either, according to your theory, the Earth is perfectly flat, or there's some form of refraction that is bending around the Earth. But again,
you got to take point, right, that this is on a frozen lake, so the refraction levels will be at a minuscule.
No, and I agree with that. They would be relatively minuscule at that temperature, and it's frozen, so I assume it's sub-zero degrees centigrade. Now, you said that the water is perfectly flat, but it wouldn't be perfectly flat because the water on a globe would, follow the shape of the globe. So the water of that lake would actually be, curved according to the globe, right? It would freeze curved. Does that make sense?
Exactly. Yeah.
Yeah.
But we're seeing the lights, though. They're not blocked by curvature.
Yeah, again, there's no the only explanation, assuming everything you're showing me is correct, and I have no reason to think it otherwise, then it would seem that would be, as they say in Star Trek, an anomaly.
Yeah, you mentioned Everest.
One sec, Dave, because I know obviously the listeners here are going to be able to get, and I know with our limited time.
Can we go over an hour? I hope we can go over an hour.
100% we can go over an hour.
Okay.
Yeah, don't worry there.
Okay.
But given that we do have what we're doing, I want to make sure that I think to this aspect, I think they have at least some understanding of the position here within this, and I want to make sure we hit some of the points that are also going to be on their minds, and precisely space. And we discussed this a bit, but there are obviously going to be some huge issues with satellites, stars, gravity, et cetera. And so I think
those are good topics for this discussion.
Yeah, I think we should hit that right there.
I want to just do one more curvature point, then we can change topics. Is that cool?
Okay. All right. Perfect. Go ahead.
Angel, you want to say something, or you want me to go? I'm going to talk about Canada.
Oh, I was ready to go for the gas pressure, but go ahead.
All right. Well, that's space. We'll go to space next. So
okay.
Here's a spot from Alusia, France, and it's a famous spot because twice a year you can see Mount Canada, but Mount Canada is 175 miles away. And at 175 miles from this altitude, which I don't know off the top of my head, but we can look it up, the top of Mount Canigou should be over a half a mile below. You paying attention, Matthew?
Yeah, I'm listening and calculating as you speak.
The top of Mount Canigou, well, you don't know the elevation height, so you can't calculate.
Okay.
The top of Mount Canigou should be a half a mile. And almost every day of the year, you can't see it. Earth curve, right? But twice a year, the sun lines up with the viewer in its migration between the tropics. And when it goes beyond Mount Canigou, you can see it. And right there, the top of Mount Canigou and the whole mountain is seen. The top should be over a half a mile below the curve. Let me just jump forward a little bit. So the globe explanation here is, that mountain is over the curve, right? And the sun is also has also set. So the sun has also set, but it's refracting up, and Mount Canigou is also refracting up and blocking the refracted sun.
Well, why don't you try infrared photography? That way you could, you should be able, with infrared, if Mount Canigou is actually visible, then you don't have to wait twice a year. You could use infrared and you should be able to see it anytime, I think. That
actually is a great idea. That is a great idea.
We have done that, but just I want to make another point on this. Now, would you agree refraction is the bending of light?
Mm-hmm.
Just simply?
Yeah,
okay.
That's a simple definition, yeah.
What we're seeing here, though, is a silhouette of the mountain. Now, the silhouette would mean the absence of light. Now, you can't refract the absence of light, but we're seeing the mountain, which means we would have direct line of sight to it.
Right. And here's an infrared shot from Malibu to Mount San Jacinto, whatever. I never get it right. I'm going to give up trying. 123 miles. That's almost 7,000 feet of curvature. This mountain is barely over 7,000 feet, so we should just see the top. But when we take off the infrared lens, blue sky, little smog, blue sky.
Yeah, infrared will allow you to see it because, again, if you're just looking at it through a regular camera. So you're saying that's 123 miles away?
Yep. Earth curve will not let you see it.
No, not at 123 miles. What is the observer height there?
I don't know off the top of my head, but it's not high. And they're from whatever 7,000 feet of curvature comes to, that's the height.
That's about three kilometers at that distance. How tall is that mountain?
Just over 7,000 feet.
Yeah, you shouldn't be able to see that.
Welcome to flat Earth.
But again, I mean, refraction could not.
Infrared cuts down refraction also. Infrared makes less refraction.
Again, I'm going with these things you're showing me. So I
and as I said, don't believe anything we say.
Understood.
Don't believe anything we say. We're just pointing out these things. And the playlist I'm going to give you, we document it all so you can see that it's all legit. And then you can go out and repeat them yourself if you like.
Well, there are experiments. I mean, there's actually some very simple experiments to prove whether the Earth is a globe or a plane. I'll give you an example. So if you have two buildings that are, say, I don't know, 50 kilometers apart. So when they build those buildings, plumb bombs, the buildings are always built perfectly vertical. So on a globe, the buildings should look like this, right?
Yeah.
Right? So at 50
I know where you're going with this. I know where you got this from too. And it's been done. The World Trade Towers were built right next to each other, right? Yeah. And on a globe, the top should be farther apart than the bottoms, but they weren't. But you can't measure accurately 50 miles.
Sure you can. Sure you can.
How?
There's you could use okay, when you use lasers and stuff like that, that might introduce issues such as refraction and things like that. But you could use those super highly accurate civil engineering GPSs. What you do, you go 50 kilometers apart to two nearly identical buildings. And if the Earth was a globe, they should do this. So you put one of those super tracker GPSs on the base of each of the buildings. You measure the distance. They're accurate within like 2 or 3 centimeters. They're crazy accurate. And then you take the same GPS and you put it on the top of the buildings. Now, there should be a difference of 50 miles probably from the top and the bottom of both buildings, maybe a meter or two, and that should be easily measurable. So that would be an experiment that should should be pretty easy to do. You just need to get your hands on those. I think they're called. I don't have a. Yeah, they're super high precision. They use them in civil engineering. They're good within a couple of centimeters. So that way, if the tops of the buildings and the bottom of the building have the same distance, then the Earth is flat. If there is a difference between the top and the bottom, then the Earth is a globe.
What do you say, Angel?
Well, you got to remember though, we've done observations like I can share it if you want. I'll just put it on screen just to show.
But just one other thing is how tall is this building? Because at 50 miles, could the buildings even see each other? And if we do see them, doesn't that prove that the Earth is not curved?
Well, according to your theory, you should be able to see them. But again, then we introduce things like refraction and things like that. But if you take the optics out of it and you use GPS, then you're not really invoking any refraction or light issues or laser measurements or anything like that. You could actually get a pretty accurate fix on them.
Well, Matthew, on screen, can you see my screen that I'm sharing?
Yes, I do.
Okay, so this is Chicago skyline across Lake Michigan. This is 57 miles in distance away from the observer. Now, this was taken at Grandmere State Park across to Lake Michigan. They're both elevated. If you calculate so the observer height is 600 feet above sea level, and Chicago skyline, the base, is 577 feet above sea level. So you minus that to get the actual height above sea level, which is 23 feet, and then you add 6 foot for the camera height, and you get 29 feet. Now, at this distance, there should be over 1,600 feet of curvature. Now, that top building there, the tallest one, Willis Tower, that's only 1,450 feet high. So the top of that building, tallest one that you're seeing there, should also be below the curve on this observation.
What is the observer height here?
When you do the calculation above sea level, it's 29 feet.
That's not a sea. Isn't that a lake?
What's the calculation above? How high are they above the lake?
Yes, that's what I need to know.
Because sea level doesn't matter, and a lot of Globers don't realize that.
Yeah.
Do you know, Angel? Is it 8 feet or something, or?
Well, his observation height was 600 feet above sea level, but the other side of the lake is also elevated 577 feet above sea level. So that's why you'd have to minus it to get the height above sea level.
All right, let's assume he's 8 feet above the lake.
No, he's 29 feet, I think, right?
Oh, okay, that's fair enough.
29 feet, yeah.
So the hidden height should be 1,700 feet.
Yeah, roughly.
Yeah, no, exactly.
What's the tallest building in Chicago, Angel?
1,450 to that top there. There's an antenna that you can't see, but it's too small to see at that resolution. But yeah,
if you look at mine, you can see it right here. Here, switch over to my screen, and I'm going to put on. This is a time lapse. Now, refraction would happen under atmospheric conditions. Atmospheric conditions change throughout the day. So here's a time lapse. I'm going to keep my finger right on this building right here. Yep. And we're going, I think this is like almost 18 to 20 hour time lapse. The building isn't moving. It isn't wobbling. It isn't miraging. It isn't changing. It isn't doing anything. It's staying exactly where it is. And we're going to go into the night and nothing has changed. We can see it all. There you go.
Wow, that must have been a super clear day.
It certainly was.
Now, that's impossible because of the distance at 52 miles.
Unless the Earth is flat.
Well, okay, I'm not ready to go there yet. But
okay, all right, wait. Here's what I want you to say, though. If you find something that's impossible on a ball, just clarify. You can say that's impossible on a globe. All right?
Okay, at 50, if these pictures are correct and those distances are correct, at 52 miles, even accounting for refraction, even if it was a 7 to 10% refraction, none of that. Was that Chicago, you said?
Yeah.
Chicago skyline, yeah.
Yeah, none of that Chicago skyline should be visible based on...
Matthew, just very quickly, that exact photo was on American news, and they were telling people that was a mirage that was refracting above.
A mirage would have to be upside down.
Welcome.
Thank you.
How could that mirage? Who said that? Who said that was a mirage?
It was, what was his name? Cooney. I can't remember his... Yeah,
was it like a newscaster or a...
Yeah.
Yeah.
Oh, well, then we can discount that.
He was a meteorologist, I think he said, actually.
A meteor, like a weatherman?
I believe so, yes.
Yeah, I don't know about the mirage thing.
So here, let me show you this.
What's that?
Hold on, wrong thing. Hold on 1 second. Let me get rid of that. So this happens a lot, and the science magazines and newspapers everywhere, they're like, floating ship, it's a mirage, and they're explaining how this ship is floating in the air, and they're giving all this Fata Morgana mirage, and it's so clear, and people are freaking out. Right. Well, so you can make up all of this stuff for the globe. Or you could actually just look at it a little more careful and understand that this is water that has wind on it, and this is water that doesn't. The sky is very nondescript. So if I crank up the contrast, I draw in where the real horizon is, I'll throw a little city there, then you could see that it's just sitting on less water that doesn't have a wind line on it.
I've actually seen this in reality, and yeah, that is not mirage at all. You just can't see the water where the actual ship is.
You can't see the water because it's reflecting. So this is another one. This was in just last year. A bunch of magazines had a floating ship up in the sky.
Well, these are just optical illusions. We can
if we crank it up, you can see the water around the ship. It's just reflecting the vanilla sky. So again,
okay.
They love using mirages, but mirages kill them all the time.
Well, I don't know. I can't comment. I mean, that Chicago skyline thing doesn't look like a mirage, but...
All right, let's shift to space.
TheWayOfWillJohn.com. Exclusive content and programs on manifestation, making money, hidden knowledge. Finally, reach your full potential. Yes, let's shift a little bit before we get to space, and I think this has already been beneficial for plenty of people that are just getting introduced to the subject. There is one thing just before we get into space, which we discussed last time, Dave, which was the movement, the speed of the Earth. What I'd like to get Matthew's understanding on. And so if you could just explain the speeds with which we were moving, and I think it's interesting just because I don't think most people know what it is that we believe to be our speeds.
The Earth is rotating at 1,000 miles an hour. No one's gone 1,000 miles an hour. You've gone 500 in an airplane. It's orbiting around the sun at 66,600 miles an hour on average. Funny number. It's chasing the sun. The sun is moving through the sky. And we're going around it, chasing it at over 500,000 miles per hour. And somehow all of the other planets stay on the same plane around, and they're all chasing the sun and its curved trajectory around the galaxy at 500,000 miles per hour. And then the entire system's moving sideways at something like 2.2 million miles an hour. That's probably a wrong number because all the numbers are wrong because we're not moving, right? So you have to believe in this crazy thing with gas balls in a space vacuum, flying in all these different directions, gravity holding everything in perfect order, never, ignoring the three-body problem, and somehow everything just works perfectly. Angel, you want to chime in?
Yeah, I just want to ask you real quick, Matthew. Turning is acceleration, right? Would you agree?
What do you mean turning?
Okay, so when you're turning, say in a plane, when the plane's turning, it's changing vectors constantly. Therefore, it's accelerating. Okay, now you would feel that motion, correct? Now,
yes,
we don't feel the Earth. We don't feel the Earth accelerating or moving, and they claim it actually does change speeds.
If all of those velocities, okay, I mean, those numbers that you threw out, they actually sound right. I think I remember those numbers seem about right. So what we have here is it's an inertial reference frame. So there's no change in velocity. Like let's just assume, I mean, there's centripetal acceleration but let's just assume that there's no changes in velocity. So if the Earth is moving at, what did you say, 66,600 miles per hour or something like that?
66,000.
It's at a constant velocity. So it's in an inertial reference frame. So no.
So really quick, the actual orbit is actually said to go from 29 kilometers a second orbit to 30. Now, if you do that in miles per hour, that's a change of 2,200 miles per hour.
You mean it's changing its velocity?
Yeah, it supposedly as it goes around the sun, it's going faster and it slows down and faster and it slows down. That's what we're taught.
We actually see the sun speeding up in the south and covering a longer distance in the south because of that. But they claim the Earth is doing it.
Okay, let's backtrack here. So if we're in a non-accelerating reference frame, so like say you're on a big yellow school bus and you're traveling 100 kilometers per hour on the highway, you can walk around, or an airplane. Let's use an airplane. If you're in an airplane traveling at a consistent velocity, 500 miles per hour or whatever, you can get up, you can go to the bathroom, you could drink wine and things. You don't really feel that you're moving, but once the plane either accelerates in the positive or accelerates in the negative direction, then the acceleration, it becomes a non-inertial reference frame, right? So
let me address that.
Yeah.
You want to go? Do you want to go, Angel?
I'll go real quick. So you're assuming that the plane is going in a straight line, though. Now, if the airplane is turning,
would be
that's acceleration. If the plane turns, that's acceleration.
correct. Yes.
So hang on. So
you would feel it.
we're in that school bus. We're on a perfectly smooth road, great suspension, going 100 miles an hour, no problem. You can drink your tea. You can go to the bathroom if they had a bathroom on a school bus. But if we got a plate of water, a dinner plate, filled it with water,
Yeah.
and that bus took the slightest turn or changed its speed the slightest amount, the water's going to go right off the plate.
correct.
Right. So we're dropping the curve of the Earth. If you're on the equator, dropping at a mile per minute to follow the curve of the Earth. If I was going 1,000 miles an hour in an airplane, I have to drop at a mile per minute just not to go into outer space. Right. If I'm in America, right, and the Earth is spinning, not only am I going, let's call it 500 miles per hour, because I'm halfway to the North Pole, we'll say, but I'm also turning because the spin of the Earth should throw me out towards the equator, right? East and west are circles on a flat Earth and on a globe Earth. They don't prove either, but they're not straight lines. And if we're spinning, I'm turning all the way around. So when I'm facing west, I should be leaning to the south because that turn should be pushing me to the south. If I had a plate of water, there should be more water on the south side of that plate because I'm turning at a mile per minute.
Hold on a second. There's some kinematics involved here. When a plane takes off, it is not taking off at zero velocity. Like it will be taking off at the initial velocity of, say, the Earth spin. So there's initial velocity relative to there's a velocity relative to the Earth, and then there's a velocity if you look from outside the Earth down. Now, when you said the plane, when it's flying, it would be did you say curving down or nosing down?
It would have to nose down.
On a globe, would have to, yes. And it doesn't do that in reality.
Yes, to maintain altitude. And they are traveling at relatively high speeds, 600 miles per hour.
Yeah, right in there.
The navigation system of the plane would have to follow the curvature of the Earth.
Yes.
Otherwise it would continue straight out into, space, right?
Can I show? I've got my my flight simulator. If you want to see it, I can show you that real quick.
Yeah, sure. That's interesting stuff.
Okay, so in reality, I've debated many pilots. They all admit they don't need to nose down in reality. Actually, I debated a pilot the other day. He was really interested and, was pretty much getting flat smack left, right, center. He had to rethink his whole world. But yeah, this is a globe. This is the actual dimensions of the globe. And if I start the flight, it's going to take off, and it's got the attitude indicator here, which maintains rigidity in space. Now, as the plane flies, I'm just going to speed it up a bit. You're going to notice that because it's curving down and away from the plane's just going to keep gaining altitude on the top.
The Earth is curving down and away.
Yeah, the Earth is curving down and away from the plane. Now, if I just leave it in straight level flight, this is how the plane flies in reality. It doesn't nose down. But because it's not nosing down on a tangent, it's going to end up in space eventually. It's going to be just gaining altitude into infinity.
Well, I don't think it has to have enough thrust and energy to get up there. I don't know if a plane, but then again, gravity is getting weaker the higher it goes, so it would require less thrust.
No, so gravity would have to pull only the nose of the plane down, though. It'd have to be selective in this case. Also,
but don't the airplane navigate, like most pilots do not fly by stick over the course of their flight path. If they're flying from Miami to Rome, they're not actually flying across the Atlantic by stick. They're using the autopilot system. Wouldn't the autopilot system simply correct for the altitude, meaning that, yeah, every minute the Earth is falling away, but wouldn't the autopilot system just simply correct the altitude to keep the plane at the exact same altitude that it needs to be? That makes sense.
It does, but over a flat Earth, because what happens is this attitude indicator has a gyroscope in it, which maintains rigidity in space. And if the plane was following
a gyroscope, yeah.
If the plane was actually following a curve, as you can see now that I'm nosing down, it's changing. It's showing a nose down in the attitude indicator on the left there. Because, and as you fly, if I've debated a pilot, right, who flew 4,800 miles with the nose up, and we've got pitch data to support this. The plane doesn't nose down in reality. It just maintains
well, you can feel it when you're on a plane. It almost feels like you're always flying with the nose a little bit tilted forward. You never really feel that it's nosing down. But I guess the question is, what about those? Okay, for those large commercial airliners, they're all teched out now. They have so much, they have autopilot systems and all that. But what about a small, regular, non-technological plane like a Cessna or something like that? The pilot would.
That makes it worse.
The pilot would have to correct for the Earth falling away, would they not?
And they don't.
But they don't.
And they don't.
A pilot has told you he does not correct for the.
Yes.
Airplanes fly straight and level over the Earth plane. Let me show you. I was on a flight to Mexico, 124 miles from the airport. Pilot goes, "We're going to start descending for the airport, 20 minutes, whatever, and we'll be there." And so we've asked pilots many times, when you do your drop of descent, your angle of descent calculation, you say, okay, I'm at 35,000 feet. I've got 125 miles. I have to figure out how many feet per mile to hit the runway, right? Makes sense. So a lot of the stuff is done automatically, but most pilots actually do the calculation themselves so they can figure it out. But this is a flat Earth calculation. At 125 miles, there's 2 miles of curvature. So if they just use their calculation, which is the flat Earth calculation, when they get to their runway, they'd be 2 miles too high.
Yeah, I understand what you're saying. I would just assume that instruments correct for that.
Well, you're assuming, but there are no instruments that can correct that. So now I'm going to show you something that we can't invoke refraction or anything. So this is a flight from Germany to, no, not this one. This is a flight from Germany to, I think, Brazil, 4,000 miles. Now, if we look at these stars here, they're just staying where they are. This plane is going a quarter of the way around the Earth. So the stars in front of it should go over their head. Here's Google Earth. This is what Google Earth says that flight should look like. These stars should be rising up because you're diving over the Earth.
Yes, that makes sense.
That makes sense. So this is what Google Earth says it should look like. But in reality, when we actually look at the flight, the stars don't rise up at all. The ones on the horizon stay on the horizon. Just when we turn, things move, but they don't rise up at all. So that defies the physical reality of a globe. You can't say refraction. You can't say anything because they should be doing this, but they don't.
How far is that flight, did you say?
4,000 miles. Now, the argument that the Globers come up with is, oh, well, you're going with the spin of the Earth spin and it's counteracting. That's not true. We're heading south. And if we were going with the spin of the Earth, that's only 500 miles an hour. So it would be going up 500 miles an hour. But the problem is they did it on the way back also. And if it was going with the spin of the Earth, now it's going against it. And those stars should be rising up twice as fast.
Yeah.
But it's not. It's the same. It's the same in both directions.
Yeah, that's interesting. So 4,000 miles. And what is the circumference of the Earth?
24,901.
Oh, wow. Yeah, there should be a significant change in the star patterns.
Yeah.
Now, here's a question for you. Okay, if you take off, if you're on the North Pole, you're and your plane is parked on the North Pole. Your plane is just spinning around on a globe Earth, right? It's just spinning
like a ballerina,
Correct, like a ballerina.
You have no sideways tangential speed. Go ahead. You're making a flat Earth argument. Go ahead.
Am I? Okay, let me ask you this question.
You're going to.
So if you're doing a little spin on the top of the Earth and you want to fly from the North Pole exactly
to Ecuador.
Yeah, let's pick Ecuador, Quito. It's right on the equator.
Right, and they have a north-south runway there. The runway's oriented north-south.
We've got a north-south, so you have no lateral velocity at all. So you're just spinning. So velocity in the X and the Y would be 0. And then you fly south.
Yeah, there would be no adjustment for Coriolis. I've debated many pilots and they will admit it.
And the velocity of the Earth rotating at the equator is about 1,000 miles per hour.
Yeah, that's that runway is moving 1,000 miles per hour sideways. So even if the plane turned to the west or the east to try to chase the runway.
Well, you would have to literally be flying sideways.
Yeah, but even if it ran at the perpendicular to the runway is going 500 miles an hour faster than the airplane's going. So the runway would just run away from him.
Let me give you another one. Let me give you an interesting one. Now, listen to this, okay? The Earth in your paradigm, okay, is moving 1,037 miles an hour east of the equator. Now, if we put a plane flying at the equator east in the same direction as your Earth is spinning, but only going 500 miles an hour, is it going to moonwalk backwards?
Well, hang on a second. So the Earth is spinning. Did you say east? Right?
Spinning to the east.
Yeah, 1,000.
Yeah. So and then the plane, before it takes off, would be moving at that same speed. So that would be the plane's initial velocity.
Yeah.
And then it would add 500 miles on top of that.
So flying east, it's going to look stationary relative to the Earth. And then but now get this, if we turn around, do 180 with the plane, go west, now the Earth is coming like this, the atmosphere is coming like this towards the plane. Is the plane going to experience 1,000 mile an hour headwind, or is it going to get to its destination 1,000 miles an hour faster? The answer is none of those.
Well, wind blows in every direction. It's
exactly
100%. So the global argument is, well, the over billions of years, the topography of the Earth has made all of the atmosphere Velcro to the Earth and spins with the Earth. So at the equator, it's going 1,000 miles an hour. In America, it's going 500 miles an hour. In North Pole, it's just spinning like a tornado.
Well, just look up in the sky. You see someday when clouds are blowing one direction, someday they're blowing the next. That doesn't
exactly.
Since we're talking about the air and the sky, let's talk about the defying of natural law of having high pressure next to no pressure without a container.
Okay, so let me do an analogy for you, okay, Matthew? So we're inside of a car enclosed. Now I spray gas in the car.
Nice.
Now that gas, due to entropy, spreads out in all directions, fills up the car. Now what happens when we open the windows of that car to the gas?
So you spray the gas in the car. It uniformly distributes within the car, and then you open the windows. Well, then the gas inside the car will blend with the air outside the car, and it will disperse accordingly, of course.
Outside. Yeah. Okay, so in the exact same way, all of our air that we're breathing should disperse into the infinite vacuum, and we'd have no air to breathe.
Well, hold on. The car, though, the pressure inside the car and the pressure outside the car are the same. So there shouldn't...
But high pressure, and it still went out.
But if there's no pressure, let's say the car is in a vacuum. We got a box of gas in a vacuum. And then we opened up top, bottom, left or right side, put a hole in it. Instantly and violently, it's going to fill the available space, just like I'm showing here.
Oh, 100%. If the car was pressurized on the inside and outside the car, it was a perfect vacuum. The moment you rolled down the windows, the air would escape into the vacuum, and then everything would equalize eventually, but...
I'm showing here we got a vacuum and we have some gas.
Yes.
And as soon as we open the valve, the gas defies gravity, because gas defies gravity, and it goes up and away from gravity right here on Earth. But we're told up in, at that, the gas gets thinner and thinner and thinner until it's a vacuum. That's ridiculous, right? It does get thinner and thinner due to temperature, due to different things, different to the atomic weight of the gases. Lighter gases go up higher, But how do we have a vacuum, a Tor 17 vacuum next to a pressurized atmosphere without a container?
That violates the second law of thermodynamics.
Let's talk then. If you have a container with two chambers and a wall separating them, and one chamber is pressurized to atmospheric, whatever, pressure, 14.7 psi, and the other one is completely in vacuum. If you remove that separation, then both chambers the air from the pressurized chamber will rush into the volume of the vacuum chamber, and they will reach equilibrium pressure. I see what you're saying. So what you're saying is, how is it possible that we have an atmosphere in contact with a perfect or near perfect vacuum? I assume space is pretty near perfect vacuum.
Yeah, 10 to the minus 17 tall.
Yeah, let's call it. If you were to simulate that atmosphere on Earth, you would need a wall like 20 feet thick. Like
Exactly.
It's okay. So what you're saying is, how is it possible for the Earth to maintain an atmosphere next to the infinite void of perfect vacuum space?
Yes.
Yeah, if we ran an experiment on Earth for that, it would not be possible. You cannot have a perfect vacuum in contact with a pressurized volume.
And the only argument that the anti-flat Earth say is gravity, but they also say that gravity's stronger next to Earth. It gets weaker as you go up.
Sure.
But I can take a straw, put it in my mouth, and create the tiniest difference in pressure by making
pressure.
And I could pull water and air effortlessly up and away from gravity, but the Tor 17 vacuum cannot.
I see your argument. It would, in a lab, you could not create a scenario where you have a perfect vacuum and a pressurized chamber next to each other. It just wouldn't be possible. Now,
but by the way, Matthew, so really quick, I can guarantee you will not find me anyone recreating a vacuum without a container using your belief in gravity.
No, I agree. It would not be possible to do it in an experiment. I mean, I've done it. It's your little picture there of what would happen. The pressures would equalize, and the air would escape into the perfect vacuum and fill the infinite void of the universe. But then, I mean, gravity. Okay, for example, we have gravity. So gravity does get weaker using, Newton's universal law or universal gravitational law. As the distance from the center of the Earth gets longer, like further away, then gravity decreases. So, but gravity
is just a theory.
Gravity doesn't affect gas laws. So your belief in gravity didn't stop the gases moving out of the car and filling up the outside of the car. Now, gas behavior is to move in all directions randomly.
Yes, that is
okay, well then, no bias for down means no bias for gravity holding gases.
And gravity doesn't pull clouds that are holding tons and tons of water in the air. It doesn't pull that down. They're held up by a different force. Walter Lewin from MIT says electric forces that hold our world together. Talk about electrostatics. I want to show you a little experiment we did. So we had where is it? Quick. All right. So we had some leftover party balloons.
Yeah.
And we tied them to, there's just a button here, and it's about 2 inches off the floor, just neutrally buoyant. Now that wire goes to a Van der Graaf generator, right? Let me just pause this for a second. And on the flat Earth, we have a neutral or negative charged Earth, testable, measurable. And then the sky is positively charged. So we have our two Gaussian plates, our flat Earth and our our positive charged sky. Anything in the air is surrounded by a positive charge, and if it's more dense than the air, it gives its downward direction by electrostatics. So right now we're going to test that theory. We're going to add a positive charge, and as soon as we do, this goes down. Now, did we just increase gravity, or do we increase the connection? We're discharging it; it goes up. We're increasing the connection. to the more positively high charged. If we take this tinfoil triangle and put a negative charge in it, it goes up, turn it off, it goes down, turn it on, it goes back up.
But that would be just, I'm assuming that's just simple electromagnetism or electrical charges repulsing and attracting each other.
It is. It is. It is. This is by MIT.
Yeah.
It's the silent drone. It's got no moving parts, and it's flying just on electrostatics. Now, are we defying gravity, or are we defying electrostatics?
No. You're not defying it. It's just the electrostatic force is greater than the gravitational force.
Good. You're helping me make my point. So they tell us that the electrostatic charge is 10 to the third. This is global science. Says the electrostatic charge is 10 to the 36 power stronger than gravity. Now, Matthew, no insult to you because no human can even understand what 10 to the 36 is.
It's a big number.
Right? Yeah. So 10 to the 12th is a trillion. Okay. Do you know how long 1 trillion seconds is, just to show you how big a trillion is? Take a guess.
I don't know, a few thousand, 10,000 years.
Very close. That's a good guess. 31,000 years. Okay. So times 1,000 times 1,000 times 1,000. That's only 18 zeros. Okay. Times 1,000 times. Yeah. So they're telling us that the electrostatic force that I just tested and proved and manipulated and scientifically experimented with is stronger than the unprovable, unscientific, unexperimental gravity that you're holding your religion to.
Religion. Okay. Hang on a second, though.
It is a religion. Okay, go ahead.
The Newton's universal law of gravitation, or universal gravitational law, whatever it's called, you can calculate force of gravity is equal to the G, big G, which is the gravitational constant, mass 1, mass 2 over the distance, or R squared. So this seems like a simple calculation of, gravity is based on the mass of the object. So that little drone thing is very, it probably wasn't, it didn't have a lot of mass to it, maybe half a kilogram, even less. But gravity is affected by mass between two objects and the distance between the two objects, all multiplied by the gravitational constant. So if you have some force like an electrostatic or an electromagnetic force that's lifting something with no moving parts, all that is saying is that that force is greater than the gravitational force that is acting towards the Earth. And the force of gravity is just the weight of the object. So for example, let me finish. For example, weight is equal to mass times gravity. So W is equal to mg. So you can calculate the weight of that object if you know its mass and you know the acceleration due to gravity, which is little g. So it's just really about a balance of the forces. The resultant force, obviously in that case, was pushing more up than the weight was pushing down. I mean, we could do these things in labs. Little drones do it all the time with their little rotating propellers. So I don't understand how gravity wouldn't work.
I know Angel's foaming at the mouth to say something here, but I just want to throw a thing.
Okay, please do foam. This is a great conversation.
It's okay. Now, Matthew, you're awesome, by the way. I really appreciate you, and you're a joy to talk to. You said that it's just a small, the silent drone was small. Are you familiar with the XRT-3B triangle aircraft? They admit that they use electrostatics to lift and propel it.
But how would you use electrostatics when most matter on the Earth is neutral? Like, for example, our bodies, this table, this microphone, it's most of them are neutrally charged, meaning that there's no net positive or no net negative charge. So when you're eating an apple, the apple is net neutral. If you remove an electron or add an electron, you create ions, but generally most matter is neutral. So how would you employ
statics?
Yeah, explain that.
Well, a Venn diagram generator adds charge and can make objects float, and no one's.
Oh yeah. If you're changing the charge, I agree. Like if you're changing the charge of an object, like whatever, then you can. Yeah, absolutely. Opposites attract. Like charges repel each other. You can play with Coulomb's law, which is strangely similar to the gravitational equation.
Thank you. So Coulomb's law is actually what causes that acceleration down due to electrostatics. It's not gravity.
Yeah, interestingly, Coulomb's law. Let me write it out here.
It's the same equation. It's almost the same as it is the same as the gravity equation.
The only difference is they use the proportionality constant instead of the big G gravitational constant.
Yeah.
Otherwise, F is equal to K Q1 Q2 over R squared. Yeah, so Coulomb's law and the universal gravitation law look almost identical. They just use different constants. Yeah.
In my opinion, the Coulomb's law and the gravity formulas hijacked Coulomb's law.
Okay, let me ask you a question then. Now I'm intrigued. Okay, so when you throw a ball up in the air, you're exerting a force to overcome its weight. It goes up, it stops for a brief millisecond, and then it heads down. So in order for it to come down, you need to have a force, because Newton's laws are pretty straightforward.
It's the law of displacement. So Archimedes' principle.
Buoyancy.
So what it is the ball is more dense than the medium it's in. So say an apple, let's take Newton's apple. It fell on his head, it landed on the floor because it's more dense than air. If it landed and it rolled in a pond, it would now float on the pond because it's less dense than the water.
Yeah, but that's simple buoyancy equation. I'll give you an example. So buoyancy is, okay, so if we have an apple, it has a weight. Weight is equal to mass times gravity. Easy to calculate. Or sorry, when I say gravity, I mean acceleration due to gravity. It's not gravity. So you have the weight of the apple, it's pushing down. Now, that apple, there's also a buoyant force pushing up, which is buoyant force is equal to the density of the air, in this case, if we're dropping an apple, which is not much, multiplied by acceleration due to gravity, multiplied by the volume displaced of that apple. So density and buoyancy are just simply it's just simply the weight of the object acting against the buoyant force. So you can't, but those equations themselves have gravity in them. Like buoyancy, when you say buoyancy, little g exists in the buoyancy equation, which is 9.8 meters per second squared. So
okay, can I get in here for a sec? So real quick, okay, how many vectors does gravity have?
Well, the vector for gravity is, well, the official answer is infinite, because every object in the universe is exerting gravitational forces on every other object. So this pen on my desk, there is a gravitational attraction to the headphones on your ear, right? We could calculate that because we know the mass of the pen, we know the mass of the headphones, we could figure out the distance between you and I. So the answer to that is that gravity has infinite vectors, but we're not interested in the pen and my microphone and your headphones. So the vector would be towards the center of the Earth.
Right. So down, one vector down towards the Earth.
Down towards the center of the Earth, yes.
Yeah. So buoyancy, though, goes up. So gravity does not create buoyancy. Now,
hold on. The buoyant force is the force opposing the vector of gravity, yes.
The little g in the formula is just acceleration. Would you agree?
Oh, I agree. Little g is not gravity. Little g is acceleration due to gravity. But remember, weight. Okay, there's two I have to write things out. So there's two equations for. You have little g, which is weight is equal to mass times gravity. Now, weight is the force of gravity, and then you have the other equation, which is the law of gravitation, which is F is equal to G m1 m2 over R squared. Now, when you do this force and you equal it to this force and you cancel everything out, little g can be calculated as 9.80 meters per second squared. So little g is directly related to big G. Now, we can test for little g because if you drop something, we can measure its acceleration. So we know that little g is correct. We know that there is some force that is creating the acceleration due to gravity. That is not even debatable.
Actually, Coulomb's law can derive 9.8 meters per second squared.
I don't know. I'm sure it could if you pop in the appropriate charges.
You admitted that the formula is the same.
No. The equation is structurally the same, but the proportionality constant Like, for example, G is 6.673 times 10 to the negative 11. But for Coulomb's law, the proportionality constant, I was just sketching it out while we were talking, is 8.99 times 10 to the 9. So little k and big G are completely different numbers, but the formula is structured the same. It looks the same, but it's the constants are completely different. And
Matthew, let me take this a slightly different direction.
Yeah.
The Earth's gravity is the same as the sun's gravity, just the amount is different. It's the same gravity. Gravity is defined the same. The sun has more gravity because it's bigger.
Yes, the mass of the sun.
It's not a different gravity, right?
Well, gravity is gravity. Jupiter has a greater gravitational attraction than Earth, yeah.
But it's the same. If Jupiter was the exact same size as the Earth, same mass as the Earth, they'd have the same amount of the same gravity, correct?
Yes.
Simple.
Yes.
So, does Jupiter's gravity affect the Earth?
Yes.
Does the sun's gravity affect Jupiter?
Yes. My pen affects your hat.
Does the sun hold on to Pluto?
Well, yeah, Pluto orbits the sun, so there is.
So the sun's holding on to Pluto. Does the sun hold on to our moon?
Everything holds on to everything. Everything affects everything until it reaches. Yeah.
Answer me this. We got our Earth, and the moon's coming around the Earth towards the sun.
Yeah.
Now, you got the Earth pulling it this way.
Yep.
You got the sun pulling it that way.
Yep.
When it goes around here, does the sun pulling it backwards? Does it slow down and speed up and slow down?
Gravity acts along direct lines, meaning it's an action at distance force. So gravity always acts in a straight line.
You're familiar with the three-body problem. We got three bodies, and they're gravitationally being modeled here. And what happens is when you have two bodies, we can model it all day and night. Supercomputers can figure out what it's going to do. But add a third body, it goes into chaos mode, and no computer can figure out what it's going to do next. Now, we have all of our planets, all of our moons, and our sun in our solar system. I don't even know how many bodies there are, like 80 different bodies.
Or maybe more, yeah.
Maybe even more. But somehow,
I think it's 120.
Somehow they make perfect. They're a perfect clock. They never change. We had an alignment this last winter where all the planets were in a line. Wouldn't something tug something out of sync? Right? The three-body problem is impossible, makes our solar system impossible, unless, of course, those lights we see in the sky are not what they tell us.
Well, as Einstein said, God does not play dice with the universe. Nothing is random.
Right. But we have laws of physics, and the laws of physics say that these large bodies, these large masses, have gravity, but somehow our sun can hold on to Pluto and ignore our moon. Somehow all the planets can line up, and we don't have to worry about the 80 body problem, let alone the three body problem.
Well, the gravitational equation, the further you get away, like distance between two objects really, really reduces the gravitational attraction between them, because it's F is equal to G M1 M2 over R squared. So when you have two like the moon to the Earth are very close to each other. So the gravity between the Earth and the moon is very, very high compared to the gravitational force between the moon.
But the sun can hold on to Pluto, which is infinitely farther than the moon, but ignores our moon. Come on, Matthew, you're making up excuses.
Well, it's not excuses. I agree. Hang on a second here. This was a respectable conversation. I agree that there seems to be a lot of chaos in the way, because you've got asteroids, you got the asteroid belt, you've got Mars, you got multiple moons, and everything is going all over the place, and sometimes it lines up. It's weird. I get it. You would be correct to think that, one day something would kind of get out of whack and everything would fall apart into pieces, right? Like any oscillating device or something like that. So it is very odd. But what is your explanation? Okay, so here let's take this in another direction. Okay. All right, so how do you explain Mars and Jupiter and all the other planets, the asteroid belts, the sun? How do you explain their movement, their size, their motion, gravity? I mean, in order for us to destroy the model of the geocentric, no, what do we call it? The
heliocentric.
Yeah, sorry. You mentioned that. So the heliocentric model, what model would replace that? Okay, so when I look up in the sky and I see the stars and I see Mars through a telescope, how do you explain that? What is that to you then?
All right. So we're seeing lights in the sky that all revolve around Polaris, east to west. Now, everything is cyclical in nature. Now, would you agree that in one day, when the sun sets, its angular size does not change? That's impossible on a ball.
Hold on. When it sets, you mean its actual visual optical angular size does not change?
Yeah, on your globe, because you're not getting further away. You're getting actually 0.0004% further away from the sun. Therefore,
yeah, it should be negligible. There should be no change in the visual appearance of the sun. Correct.
Okay, so if I could show you more than 3 videos, me personally taking videos of the sun, a sunset with a solar filter, would that change your mind?
I don't know. Hit it. Let's see what You freaked me out a little with the mountains and the boats. So let's see what you got.
Okay, so according to the globe paradigm, the sun cannot change even 1%. But I've personally got upwards of 23%, and buddies of mine have got with the solar filter upwards of 40% change in the sun setting. Now, it doesn't look like it changes very much, but when you actually zoom into it and count the pixels, it does actually change quite drastically, especially this one. This is my 23% that's going right now. You can see it changes size. And this is with a solar filter, pretty powerful solar filter, ND1 million. This one was a short one, but even this one changed size if you really zoom in.
But couldn't it just be atmospheric distortion? You know what I mean?
It would be magnifying. It would be magnifying on a flat Earth as the sun goes away. It is magnifying because it's going into more and more moisture, but it still gets smaller.
Well, if something goes further away, it should get smaller.
Right, but it is getting smaller, but it's also magnifying. And on certain conditions, if you watch the sun, it will just go away and get smaller and smaller. And it's not going down; it's going beyond. And it's going to just set beyond this cloud, this atmospheric horizon. It just goes, it gets smaller and smaller.
So you're proposing that the sun is not going up behind the horizon. It's simply disappearing from view based on perspective.
Exactly. Perspective and atmospheric occlusion.
Yeah, that could, optically, that works. Yeah.
Watch this. I've got another video that clearly demonstrates this very easily, what you just said, Matthew. So here is the same video that Dave just showed you. Now, I've overlaid a hole on top of the ocean to show how our eyes work and why the horizon is actually there. It's due to eyesight, not Earth curve. Now, I've overlaid them both. Now, watch this. It displays perfectly why the sun sets.
Yeah, listen, guys. Optically, like it is possible to simulate something setting by just simply moving it further away. We've seen this. Like things disappear. They look like they fall below the horizon as they move away. Optically, visually, we see it. So I guess, hold on a second. So these things can be explained through optical phenomenon. So yes, the sun can set without really setting. To our eyes, we can see that. Now, the sun's size should not be changing if we are, 95 million miles away or something like that? Oh, is it 93? Okay, so there shouldn't be any marked change in its size. I mean, there is the possibility of atmospheric conditions, which would cause something to appear bigger. Have you ever seen the moon? Like, there are some days during the year that the moon is like 3 times bigger than it should be.
Hold on. Listen to this, Matthew. This one's going to freak you out.
Yeah, let's see it.
No, I'm not going to show you.
Oh, okay.
Next time you see and Will, you too. Ready? Next time you see a gigantic moonrise on the horizon, turn around backwards, spread your legs, bend over, and look at the moon upside down through your legs, and it will be tiny. Your brain short circuits. When we see something near the horizon, it looks bigger.
Really?
Right? But if you flip around and take a mirror, it's like, wow, look at that moon. You take a picture and you're like, God, that's tiny in the picture. because the illusion's broken in the two-dimensional picture.
Okay. All right, optical illusions aside, this is fascinating. Hold on a second. What is the moon and the sun?
Hold on. As you hold your finger out, I can hold my finger and block the moon at the giant moon. And then later when it's tiny, I can do the same thing and it's the same size. My finger blocks the same moon, even though it looks much smaller. It's the way our mind sees.
No, hey, the mind is a funny thing. I get that. Like the mind can play tricks on us. I get that. That's okay. So wait a minute. So what are you proposing? What is the moon? What is the sun? Are you proposing that the moon and the sun are not what they appear to be?
I know for a fact that the sun is not a giant gas ball in an infinite vacuum.
You said as a fact. Can you? How do you?
Yes.
Because that.
Can I just get, let me get this in just so we have a clarification of that, though. Okay, which is perfectly fine. Doesn't state that we are stated. It has been stated that the sun is a giant gas ball, correct? Now, you're saying that it's not, and you have, you have something that you believe to be fact. So then what exactly is it? And then I'd like for you to explain Matt's question on what the sun and the moon are.
Okay, so I wouldn't make I would not make a positive claim on what the sun is because we can't science the sky, but I know for a fact that it's not in a second law of thermodynamics violation. So therefore it cannot be a gas giant in a vacuum.
Matthew, if I had a box of helium in a room that had no air in it and I opened the box, the helium would violently fill the available space, correct?
I wouldn't say violently.
Well, it would rapidly. We'll say rapidly. Okay.
Well, if it was at the same pressure as the air, it would eventually.
No pressure. Zero on a vacuum. And the room is a vacuum. The box has the air in it.
Oh, violently. Violently would be correct then. Yeah.
Okay. So gas always fills the available space.
Yes.
Right? Okay. And that's what it does. Low pressure gas, high pressure goes to low pressure.
Yeah.
So helium and hydrogen defy gravity here on Earth. They tell us the sun is 99% helium and hydrogen. How much helium and hydrogen do you need before it decides to collapse into a star?
Well, hang on a second. Helium and hydrogen don't defy gravity. They are light. Their weight is less than the buoyant force.
Let's pretend the universe is completely empty and I have an Earth-sized bucket of helium and I dump it into the universe. Is that enough for it to collapse into a star, or is it going to fill the available vacuum of the universe?
Well, if it would fill the available vacuum.
So how much helium and hydrogen do you need before it collapses and becomes a furnace? Like a sun, whatever you want to call it, right? And the answer is there's no answer. Okay, there's no answer. Our sun burns 640. This is what they tell us: 640 billion tons. It's either an hour or a day. Doesn't matter.
That's a lot.
Okay. 640 billion for billions of years. It never gets any smaller. Where is it getting this fuel from?
Well, eventually it will get smaller, but
and that's a cool story, bro. But that's just a made up story. We have helium and hydrogen defying natural law in a vacuum, burning unimaginable amounts per day, never getting any smaller.
Well, it's not burning; it's a thermonuclear reaction. But
that's cool.
I get your point.
Yeah.
The world record for nuclear fusion is, if I'm not mistaken, is only 40 something seconds, and it's been doing it for a billion.
I didn't even think it was
billions of years.
40 milliseconds, but yeah.
Yeah. Okay. Either way.
Okay, and the sun's been doing it for billions of years,
and it's never getting any smaller. And how did it stop? And we're told that suns and stars come from nebulas, gas and dust in a vacuum. That's another problem. And all of a sudden it creates a star and then it spits it out like a ping pong ball machine. And that star just runs and finds a little place to park itself. Why doesn't the entire cloud collapse into a giant star?
Gravity, man. Gravity,
dude. Matthew.
That big G, man. We need that big G.
You're a smart guy. You have and by the way, you have a lot of, and this is not an insult, a lot of indoctrination. The way you get your degrees that you have is you memorize and repeat what they tell you. All right. Now we're challenging you here to look at some of the things that you were taught. Some of them are not true. Science is always changing. The sun used to be 3 million miles away. Then it was 6 million miles away. Now it's 93 million miles away. Right. I say the sun is just a couple miles away.
Couple miles?
I don't know what the sun is. I don't know how far it is.
Okay, a couple of miles, man. You could take a drone and no, it can't be that close.
It's in an apparent position. Go ahead.
Okay. How far away are clouds, Matthew, would you say on average?
Oh, I don't know. There's different layers.
Just pick a number, random.
Some are really low. I'm driving on the highway. They look like they're only like a kilometer up, but others are, I don't know, 50, 60, 70, I don't know. something like that.
Right. I don't know why I can't share my screen properly. Hang on. Where's my video?
Well, there's different types of clouds. You got the cumulus, you got the whatever the other names are, right? I'm not an atmospheric physicist, but
Yeah, are you trying to show this picture here? This one?
No, I'm trying to share my own video. Oh, here it is. Yeah, here it is. I got it.
Is this sun 93 million miles away?
well, it doesn't look like it, does it?
No, it doesn't. All right. There's no proof of anything. I can't make any claims.
So Matthew, how do you have a local hotspot, the moon creating a local hotspot in the clouds? And also, when I zoom in, it's obviously around thick clouds, and you could see the face of the moon clearly. Watch this.
Let me see. What am I looking at here? So that's the moon.
This is the moon. Yeah, look at that local halo. Like you're getting a local halo around the clouds, which means it can't be that far away.
Well, it's a visual perspective. Our eyes are, I mean, if somebody was looking at it from a different perspective, they would see the same thing only oriented towards them, right?
Right. But look at this. How do you get a local light like that and you could clearly see the face of the moon there, Matthew? I don't know, man. In my opinion, with my naked eye, I could see that moon was in front of the clouds there.
Right. And this moon right here, if you could see my screen, is lighting up this area of clouds. If the moon was 250,000 miles away, it would light up all the clouds equally, but it's lighting up the ones that it's right near. Now, listen, we don't know what the moon.
Yeah, when you see the sun shining through the clouds, it does look like it's shining in one particular spot. But if the sun is 93 million miles away, you would think logically, just even if you knew nothing of science, that it would not create a single hot spot. It's
the sun rays, because the sun's so far away, the rays come in parallel, correct?
To the Earth? Yeah, for sure, because it's 93 million.
But why do they always look like this? Why do they always look crepuscular?
Sorry, could you? I understand where you guys are going with this, but then what is the solution then for where exactly the placement of the sun is if it's not 93 miles?
So we're just looking at evidence, and the sun that we see is in an apparent position. Matthew, if you and I were standing at the beach in Angel, we're all 100 yards apart, and we're watching the sunset. You're going to see the sun walking on the water, that beam of light on the water right to your feet.
Sure.
I'm going to see mine, and Angel's going to see his, but we won't see each other's. We'll all see the sun in a different position. We all have a personal relationship with the sun.
Yeah, I've seen those little angled rays when I'm driving on the highway. You could see it looks like it's right above the clouds.
You never see this. This is what it would.
You should see that.
This is what you should, but you don't. Welcome to Flat Earth.
Yeah, but wait, hang on a second. But couldn't that just be the way the cloud? Like it could be when the light comes down parallel. The clouds could be just simply, clouds can take various shapes. It could just be deflecting the light sideways.
Can you see my screen? So on screen, I've got what the glow paradigm claims is that it's like train tracks converging. Now the problem with that is the train tracks are coming towards you. For a train track to converge like that, it has to be coming towards you. Okay. Now, when we have vertical lines going up, like those, the Chicago skyline I showed you earlier, that's not diverging, right? These crepuscular rays are not coming towards our eyes. Therefore, perspective is not in play, but they're still diverging, proving that they are actually crepuscular.
Right. If you look at this picture right here, stop sharing for a second, Angel. So we got the sun, the rays are coming out. Now, these rays going into the distance, they're still diverging, but they're going farther away from us. So perspective is trying to bring them together, but they're diverging so much that we can still see that they're diverging, right? So we have diverging rays here. That points to a very, very local light. And again, Angel and I, we don't know what the sun is. We don't know what the moon is, but we know what it's not. The moon is not a dusty, dirty rock reflecting sunlight, right? The moonlight is actually colder light. The moonlight, when you magnify it, is colder.
Wasn't there a song about that?
Probably.
Cold moonlight, something about
so
that.
The moon, and on a full moon night, it's usually colder than not.
Whoa. So what you're saying is that an object under moonlight
is colder than under moon shade.
Colder than an object in total darkness?
Tons of experiments done showing that.
Well, that should be easy to experiment. You just need one of those thermometers.
We've done it. Done 100 times. And by the way, There's 100 ways to do it to get a false reading. Some people will like put a piece of cardboard to shade the ground, but that's now insulating the ground. That's not fair. You can't do that.
Well, I have one of those thermometers. I should give that a shot.
You can do it where you have the moonlight. Let's say it's on the pavement, and then there's a vertical fence not insulating the ground, and there's a shady spot. Then you can do it, and you'll see a dramatic difference.
Well, anything under moonlight should be a little bit warmer.
Colder.
No, it should be warmer because it's
on a globe. Yes.
Wait a minute, on a globe. Okay, so let's backtrack here. Okay, so this is actually has nothing to do with globe versus flat. So now we're discussing the nature of the sun and the moon. So are you saying that the moon and the sun are, so the moon's not 240,000 miles away and the sun is not 93 million miles away?
Correct.
Okay, so this would then affect the diameter, the diameter of the sun and the diameter of the moon, because they can't be whatever size they are. I wrote it down here.
Hold on, let Angel speak.
All right.
Okay, you believe that the sun is 400 times bigger and further away than the moon, though, but they appear the same size, right?
Whoa. So you said that the sun and the moon are...
They tell us that the sun is 400 times bigger than the moon and happens to be 400 times farther away. Therefore, they look like they're the same size. That's what you believe.
Okay, where are you getting these? I'm calculating. Okay, so yeah,
that's your paradigm. That's your paradigm.
Yeah. Okay, so yeah, the moon. I'm just doing. Okay, so the moon is 400. Sorry, the sun is 400 times greater in diameter than the moon. Okay, got it.
And further, so that it appears the same size as the moon.
And the Earth and the sun is, did you say 400 times further away?
400 times bigger and further, yep.
Oh, that's coincidental.
Very good.
Yeah. Just wait till I tell you how the moon formed in your model. Yeah,
you're right. I just ran the diameter and the, it's 400. Yeah, it's basically 400 times bigger and 400 times further away.
And somehow they magically line up for solar eclipses on a repeating cycle every 18 years.
That's quite the coincidence, isn't it?
Welcome to Flat Earth.
Or Matthew, maybe they just are the same size.
Okay, wait a minute. But they optically, visually, they are the same size. That's why we have eclipses.
And maybe they are the same size and the same distance. You know, when we zoom in on the moon and bring it into focus, we can zoom past the moon out of focus. We can zoom before the moon out of focus, on the moon in focus, and then we can shift to a planet or the sun, and they're in focus also without changing the focus. They're all at the same focal length.
Well, God does not play dice with the universe. Nothing is random. So 400, that's an interesting number. So that's why they appear the same in the sky.
Okay, Matthew, check this out. If you think that's a coincidence,
it is a coincidence, but yeah, okay.
The curvature rate of your globe is 8 inches per mile squared, or 0.666 feet per mile squared. The tilt of the Earth is 23.4 degrees, or 66.6 degrees, when taken from a right angle. The diameter of the moon is 2,160, or 6 times 6 times 60. The circumference of the Earth in nautical miles is 21,600, 6 times 6 times 600. Now, I don't know how many more sixes you want, but I can keep going if you want, but that's a lot of sixes.
Are we talking number of the beast stuff?
It's just weird. It's just weird. The whole helio-satanic model is filled with sixes.
All right, let's stick to Newtonian mechanics, but okay.
Let's shift slightly.
I want to talk about stars and the sun, the size, for just 1 second.
I agree, and that's fine, and we can definitely continue there. But there are portions of this that I still think need to be addressed while we have both of you here. Ones with which we discussed in our first discussion, Dave, which has to do still with, as you guys are moving into space, but simply just talking about these large planetary objects out there. But I would like to focus a bit on, as you said, the current paradigm and who's giving that information. Obviously, Angel, you're citing NASA, where a lot of these numbers are coming from. And I would like to take this chance to give an understanding of if the flat Earth model is the correct model, or if the heliocentric model is the correct model, what's going on with then launching into space, if people are in space and on the moon specifically. So if you guys could maybe just shift the discussion there to whether or not the astronauts have any issues physically getting to the moon.
We can do the rest of the show on fake space. Let me just show this one more point for Matthew, because I think it's going to resonate well with everybody.
All right, let's give it that one more point, and then let's shift there, because I think people are definitely going to have a chance.
The sun is 860,000 miles across. It's gigantic. If it was a mile over your head, it would look like that, right? It would just fill the whole sky.
Yep.
Agreed? Okay, so we got the moon, we got the sun. It's a mile away. We move it 93 million miles away, or 8 light minutes. That's how they say
8 light minutes. Yep.
8 light minutes. It's now the size of a coin held at arm's length.
Yep.
Okay, so if I doubled the distance again, it would be half this size.
Yep.
So now it's 4 times as no, it's twice as far. I double it again, 4 times as far. It's a quarter of that size.
Sure.
I double it again, 8 times as far. It's now a 16th of that size, which is like a ball bearing. It's like smaller than a pencil eraser, like half the size of a pencil eraser, right? So it's now approaching the size of a large star. So 8 times 8 is 64. We'll call that 8 times the distance, 1 light hour. If we made it 2 light hours, I doubt you could even see it. Let's make it 24 light hours away. You can prove that its angular size is too small, and forget the inverse square law of how bright it would be. It would be dimmer, dimmer, and dimmer. But we can ignore that. At 1 light day away, you could not see the sun.
How are we seeing stars 100 light years away?
You're not. So this is my point. I'm going to make that point exactly. You're already jumping ahead.
Oh.
So at 1 light day away, we could not see the sun. They tell us Polaris, that we can all see with our naked eye, is 46 times bigger than our sun. So if we put Polaris at 46 light days away, let's round it up to 2 months. Give the globe the benefit of the doubt. At 2 light months away, you could not see Polaris. Round it up to a light year, right? You could not see Polaris. But they tell us Polaris is 433 light years away, and everybody can see it with their naked eye.
Is that how far it is? 433?
Light years.
Uh-huh.
And now the most important star in the sky, they're saying, well, maybe it's only 333 light years away. 100 light years. Okay. You can't even fathom what that is. But I just proved, giving the globe a huge leeway and benefit of the doubt, that at 2 light months away, you couldn't see it.
Yeah. I mean, it's like taking a school bus. Yeah. How do we see satellites? Yeah.
Oh, well, all right. Satellite, that goes right into fake space. Well, we're on track.
There you go. Okay, great.
Oh, is that where we're going? Fake space?
Yeah. You were going to fake space and satellite.
Oh, this is all about the moon landing and stuff, right?
What moon landing?
Okay.
Wait, we landed on the moon?
Didn't happen.
Oh, really? Okay. Okay.
Let's hear what is fake space? Let's start there.
Yeah.
Yeah. Matthew, have you ever seen the Starlink satellites? Have you ever looked up and see the line of satellites?
You can't see satellites with the naked eye, so no.
People say you can. I saw them. Starlink, you can.
Take a medium-sized car and
I'm with you.
And drive it 500 miles away and tell me if you can see it.
I'm with you 100%.
No, satellites from the perspective of physics, unless they have some kind of illumination, which they don't, cannot be seen by the naked eye.
We gotta get him on the lives working with us.
Wait a minute, hang on a second here, guys.
You got to come over to Angel. He's on TikToks.
No. Okay, maybe.
Matthew, I want you to remember.
All right, no, I have never seen the Starlink satellites because it's impossible.
What you just said is true.
Yeah.
Okay, but here they are. And I've seen them myself. Now, this was 2 years ago. I saw.
No, those can't be satellites.
I'm with you, but this is what they tell us they are.
Balloons, maybe?
They're local. They're not far. They're not far away.
Drones?
Yes. Don't know. Not sure. But they're not satellites because, as you pointed out, the Starlink size is smaller than a 747's engine, way smaller, right? So here's a 747. You can barely make out the shape of the plane when you're looking at it, but you can't see the engines. The plane's only 5 to 7 miles up.
And why are the satellites illuminated? Why do you need illumination on satellites?
Well, that's reflecting sunlight, they tell us.
They say it's the sun. Yeah, that's the sun's hitting it.
If this is 7 miles high, if I made it double the height, you couldn't see the airplane, right? But the satellites, these tiny little satellites, are 350 miles up.
Is that their altitude? 350?
350, and then those lines, they're telling us that line of lights is satellites.
No.
Is Starlink satellites.
No.
See, here's the thing. You can't even believe your own model because you don't know it. Because when we point out these things that your model, your paradigm says is a fact, you're a smart guy. You're like, that's impossible.
All I'm saying is there's no way you could see those Starlink satellites with the naked eye.
Welcome to Flat Earth. Welcome to fake space.
Hang on a second. Wait a minute. Hold your horses. That doesn't prove the Earth is flat or not flat. So how does this satellite thing tie into your theory of a flat Earth?
Let Angel talk. I've been talking too much.
Okay, well, the satellites and everything that they claim is up there is not in a second law of thermodynamics violation. It's not far away. It's local.
Hold on. Second law. Wait a minute. How are you connecting this to the second law of thermodynamics?
Okay, well, according to what we said earlier, all the gas should just disperse into the infinite vacuum. So a vacuum doesn't exist. It's not in the sky.
Well, second law is more the law of entropy, but okay.
According to the law of entropy, all of our gas should disperse.
Okay, but how does that relate to satellites?
Well, they claim it's in a second law of thermodynamics violation in the space vacuum, which doesn't exist.
We talked about that before. High pressure next to low pressure without a barrier.
So wait a minute. Let's backtrack here. So space does not exist?
Correct.
As described.
The vacuum. I mean, we have things up there, but they're more local, right? Remember what I said earlier. My position was that.
But how do those things rotate? Okay, if your Earth is a flat plane and it's not a globe, how do those objects like the ISS or the satellites rotate around the Earth?
If you go look at the trajectory of the ISS, it perfectly matches a ring magnet ferrocell. So it does a perfect spiral of pattern, and it never goes over the poles again. So
you acknowledge the ISS exists?
No.
I admit that there's got something up there. It's not in a second law of thermodynamics violation. There's no people on it.
So I have an ISS tracker years ago before I was a flat earther. Oh my God, the ISS is going to go right over me here in Connecticut if I live in Connecticut. And right on cue, it showed up on the horizon and I watched it. It went right over me. So when it was over me, that's as close as it's going to get to me. Would you agree? Straight line up. Right? Because when it's on the horizon, it's farther away.
Yeah.
So it's 250 miles directly above me. Now I could see it for another, I think it was 4 or 5 minutes, 17,000 miles an hour. Times 4 or 5 minutes. What's that come out to? It was like 3,000 miles away. I could still see it when it's over California. It's the same size as a 747. How could I possibly see it 3,000 miles away?
No.
Okay, I did though. Therefore, what I'm seeing isn't that big, isn't going that fast. It's fake. Now we had NASA whistleblowers, but again, it's all hearsay.
So what is it then?
Well, the thing that we see,
like a balloon?
No, this one NASA whistleblower said it's a B-2 bomber. They have 5 of them with some parts are transparent. They have LED lights on the bottom and they take turns. 2 of them are based in Alaska. One's in, I forget where they are. And they literally take turns. So there's certain times where you're watching and all of a sudden the thing just disappears.
But why? Why are they faking the ISS?
Why the lie? We'll get there.
To keep the lie alive. Now, also, the ISS, if you really want to know where it is, it's in a pool. It's called the Neutral Buoyancy Lab.
Yeah, that's where they do the astronaut training.
Yes.
Yeah, the ones where they fake the footage, you mean, because we see the bubbles in space.
Oh, we do?
The what in space? I'm sorry? The what in space?
Bubbles in space. There are bubbles in space.
Huh. Do we have any documentation of that?
Can we clarify bubbles in space real quick?
We have tons of footage.
Really?
Yeah.
Oh yeah. In the live feeds.
Wow.
So this is a ISS live feed, right? Right. This poor guy's hanging off of a cliff, right?
Yeah.
NASA gets $84 million a day. Sorry, $84 million a day in budget, right? And that guy is just playing with a stupid green screen. They couldn't possibly be doing that.
Yeah, but anything like this is Hollywood. Like, look.
This is NASA. This is NASA right here.
Yeah.
Okay. This is them in a pool, and this is them in space.
So you're saying that all of the astronauts that we see on the ISS and everywhere else is all just either in a pool or in a green screen?
Yep.
They're acting.
Yeah. Yep. And they all are in on it except maybe Don Pettit. He probably believes he went to space.
So every astronaut essentially is in on the lie of this construct.
100%.
Except Don Pettit. He might actually believe he went to space. You have to give me that one.
Would you guys agree that photos and videos from Narnia don't verify Narnia? If I was to show you a live feed of me in Narnia, would you believe in Narnia?
No. We all know that Hollywood has the technology. We've seen movies like Gravity and Interstellar. They're phenomenal. They look perfect. So there's no question that any of this can be doctored. We know that.
Do you remember this spacewalk? So you got this guy out here. They're going 17,500 miles an hour, and he goes away with his little jetpack, and he comes back. So a couple years later, they did another one, and hold on.
Yeah, but his initial velocity was the same as the spacecraft. So
No, I'm with you. I'm with you.
Yeah.
So there's the first one. And then the second one that they show us, and they only show us a picture, you can't even tell the difference. It's just the Earth change. It's the exact same pose, the exact same thing. And when I look at them side by side and I zoom in, it's the exact same image. So again,
well, in all fairness, they're probably using the same spacesuit. So
I'm just saying.
Yeah, it does look like it's a cut and paste. Yeah,
it is a cut and paste, right? So I want to just show you
what did Elon Musk say when he launched the Tesla Roadster in space? He says you can tell it's real because it looks so fake.
Yeah, you can tell I'm really not in space because I look just as good as the astronauts right now. I'm floating on the space station.
I remember him saying that. I'm like, what? All right, what do we got here? Is that the ISS or is that?
I'm on the ISS. Come on. I'm holding on with my feet so I don't float away.
Okay, but that looks fake. You look fake.
Well, it is fake. It all looks fake. But here,
yeah.
What about this? Check this out. This was a live feed, and the guy just appeared out of nowhere.
Hey, that looks green screen then.
No, well, that does. This was a live feed, and it happened.
Maybe a glitch. Maybe it was just a glitch.
A glitch. Explain where he came from, unless they're using multi-layered technology.
Well, maybe they got a Star Trek transporter.
Right, here's this guy faded out. Same there you go. Right, and then
are these legit ISS videos?
These are again. This is from an ISS live feed. Look at this line. What is this line here?
Wow, that's a real cloudy day on Earth.
But look, that's what they show all the time. Cloudy days on Earth. But where is this line?
Stitched photography.
It's stitched, right? So they're not showing us a lot.
But they have to do that sometimes, don't they?
Well, why would they? They're flying over the Earth, point the camera down, and live feed us.
Yeah, that's true.
Right.
This is very suspicious, guys. Very suspicious.
I'm just gonna hit a couple more, and then Anthony's. Okay. Not Anthony. Angel's got some things. So a lot of times when they're doing these clips here, sometimes they're hanging by wires. And sometimes they're in a pool. If the spacewalks are in pools, sometimes it's green.
Oh, they're not in pools here. They're obviously not in a.
This is not pool. This is hanging by wire. But it's a little hard to see. You can see. Look right here. You can see the wire pull from his shirt.
Hey, there it is. His little harness.
Yeah. And there's some of the others that are way clearer. But I want to just show you a couple things. Right. This is they had their Christmas hats, and that was in 1999, but then in 2023, gravity didn't apply. Their hats became anti-gravity.
Well, the little top of the hat shouldn't float up automatically. It doesn't.
Well, why are they all down?
Well, yeah.
And why are they all up? Why are they all down?
And why did the women use hairspray?
Why are they all up? Down? Why are they all up? Hold on. There's one more I want to just.
Is this on the ISS?
This is on the ISS.
They have nothing better to do than this.
Well, right, and other things, right? So they had a little green screen glitch where everything orange turned blue and everything blue turned orange. All right, that just shows again that they're using technology. Here's Kamala Harris talking with the ISS, and I
can't even get cell service in my basement.
Look at this wire going right through their hand. They're always playing with something. This is called augmented reality.
So this is like some kind of VR glasses thing?
Well, that's a good point. They used, we got somebody whistle blew and said that they're wearing Microsoft HoloLenses. So the top half, they're literally behind these like snow goggles, but their faces are mapped with AI technology, and it's tracking their eye movement. So we don't see they have their goggles on, but when they're playing with the augmented reality, you'll never see them wipe their face.
Okay, in all fairness, just hold on for 1 second. These are all digital feeds. We know that digital feeds do glitch out sometimes. Like, we've been in Zoom meetings, things glitch out, things res, people's faces disappear. We can't really take a look. Okay, this guy coming in and out of view, these things moving, these could be these are all digital.
Matthew, let me show you some more.
All right.
Right? Look at this lemon. Is that a real lemon or is that an augmented reality object? Look.
Yeah, it looks fake. Yeah.
It is. It's fake as F.
It looks fake, but again.
Right. And then Don Pettit, the one that probably thinks he went to space, said he was tired of drinking coffee out of a bag, so he created a cup. Now watch the coffee color in here, and all of a sudden it gets out of sync. Bam, it's over here now.
Yeah, but could that be a digital glitch?
A digital glitch makes the brown jump out of makes the brown jump out. Right?
Yeah,
Wait, here, hold on. You can make excuses all you want. Here is Chris Hatfield, and this guy, look, he's upside down. These guys are in different studios. He holds the mic in the wrong place, and it goes inside of his neck. Now, look, the microphone is in his neck. Now, you could say, well, cosmic rays and digital artifacts. You can make all the excuses you want.
Yeah.
But right. And then again, it's in his neck. This guy, watch under his right arm. He moves a little fast and he reveals the green screen. And watch, ready? When he brings his arm down, you can see the green screen right there. Okay.
Yeah.
So again, you catch them once.
Okay. Why would they be faking? Whoa. Did that guy just go by on a harness?
Yeah, thank you.
Yes.
They forgot the layer that was supposed to hide the harness. And then
Jeez, I saw that. That jumped right out.
Can I ask one question before we get to the lie, Dave? Just specifically to you as well, and Angel as well. If you could address this one, this one's less from Matt, but it does lead to where we need to go here, which is why the lie. But before that, given that they do, let's say, according to this model, they are faking everything in space. NASA is in on it. I would assume many elites, governments. I mean, it's a massive cover up if it is to be like this. How are we going to account for guys in harnesses and horrible green screens and all of these things as negligence, incompetence, or what is how? I mean, if I'm going to get this huge elaborate lie going, I mean, surely they can pay for a couple interns to go, oh, we messed up. Yeah, you can't send out that green screen shot. Why leave any mistake in whatsoever?
Go ahead, Angel.
Well, we don't know why we know why they're lying, but the thing is we catch them out and it's too late, right? They've already done the lie feed.
But I don't understand how it could be. $84 million a day, you said, right?
Hold on. So I thought Angel had a different opinion. My opinion is, I don't know. Either it's stupidity or it's revelation of the method. They always want to tell us the truth so not to break our free will. They're like, well, we made it kind of obvious. It's, they think that it absolves them karmically. Right. So and then lots of times we caught them. We caught Elon Musk on one of his rocket landings where the two rockets were landing, where they screwed up and they had the same feed from both. They literally changed the live feed that night. They changed it and it never said changed. And YouTube doesn't allow that. It had millions of views, not allowed to change it. They literally re-edited the live feeds and it never said edited. So look at this ball. This ball is like a balloon and it's neutrally filled with helium and air and it's neutrally buoyant. Are you watching, Matthew?
Oh, yeah, I'm watching.
Okay, so watch up here. Where did that come from?
It beamed in, but that's special effects. They did that on purpose to be cute.
No, they didn't.
Star Trek transporter.
No. So that actual little beam thing you did, it's from a Microsoft product. I forget the name of it off the top of my head. That's the transition thing. And they accidentally left that in. But the fact that it's not here, they're talking to kids.
Oh, I see what you're saying. So okay, we see that they have the technology to okay, I see what you're saying.
Yeah. And so she was manipulating this thing. It's called Paxi, and she's manipulating it, right? And so it's augmented reality technology where.
Look, guys, look. I'll be honest with you. It does all look fake. I get it.
It is all fake.
It looks bad, like Interstellar and
The movies
The
look
movies
better.
look better. And, but, you know, like, what's his name? Like, Matt Damon said in The Martian, you know, we're going to have to science the shit out of this, right? Like, it's, look, okay, these special effects, okay, these things look bad. They do look fake. I admit it. When I saw the Tesla Roadster in space, it looked completely ridiculous, but it is what it is. So there has to be some kind of motive for this. All right, so
we're gonna finish with that when we get there.
okay, well, yeah, let's not get there yet. But like, if the Earth is flat, fine. Okay, why are they hiding the Earth is flat? I mean, if there's no space, we didn't go to the moon is not the moon, the sun is not the sun, we don't even know what the stars are. I guess if you're in a planetarium, you look up, it simulates the same thing. So could you really tell the difference between a planetarium and the real world?
No.
I don't know. But there has to be a reason why they do and again, I use the term they. I don't even know who they are, so I'm just going to be careful here. But this is a very, very, very elaborate global. If what you say is true, and again, I'm being very neutral here as a physicist, but if what you say is true, there is a tremendous amount of resources pumped into, like, faking the moon landing is, yeah, sure. Could they do it? Yeah, I could probably do it now with some technology, but back then it was probably a little harder. But I guess the question is, like, why the hell are they doing whoever they are doing all this? But we'll get to that. I'm very interested in these things you're showing me because they actually look a little bit crazy. Not that you're crazy, but they look so bad that.
Do you want to see one more?
Sure, man. Bring it on. Bring it on. I love this stuff. This is what science is all about. You have to question things, right?
Matthew, again, another compliment to you. You are actually using science and admitting.
Well, this is science.
Yes, I appreciate it. Go ahead.
You know, people thought Einstein was crazy until he wasn't. People thought Newton was crazy until he wasn't.
You know what E equals MC squared means?
Yeah, energy is matter times the speed of light square. Yeah.
No, it's actually Einstein married his second cousin twice.
Oh, God. All right, boys.
All right, check this out. Okay, so this is an actual real time lapse of the stars from the ISS from Don Pettit. Now, on a globe, if you're on the globe and you're spinning, and therefore it creates the illusion of the stars spinning.
Yeah.
Okay. So now we're flying around the Earth at 17,000 miles an hour, and we're looking at the star trails. Now, watch. There's a major problem in this. Okay. When it faces towards the north of the ball, let's say, so these lines here on the Earth are going sideways. But why are these star trails still doing circles? Do you see that? Why would they be still doing circles if you have to be attached to the Earth and for that to be spinning? Do you see the problem here?
What are those lines going east to west? Is that that's the spin of the Earth?
Yeah, so this is the ISS flying in space above the Earth, but these star trails are still doing circles. That's impossible. It should be streaks of light because the stars aren't spinning in your paradigm. You have to be on the Earth, attached to the Earth, and looking up at the stars for them to spin.
Yes, the stars spin around Polaris, the North Star on the Earth. Yes. Well, actually, the Earth spins. The stars are fixed.
Exactly. So it should not be doing circles if you're flying sideways relative to the stars and doing a time lapse.
Is this real, though? This looks fake, too.
Yeah. This is claimed to be real.
I don't know why those stars would be turning that way. I haven't given it much thought, so I got to be careful with what I say because, you know, I need sometimes time to sit down and look at things. But what is this?
This is the Georgia Guidestones where it's got a hole in it pointed to Polaris. And my friend Nathan Thompson did a time lapse.
Wait, they got blown up, didn't they?
Yeah. Because they prove flat Earth. So this is what we see from the Earth according to the globe paradigm.
So wait a minute. So the Georgia Guidestones had a little hole in it that point to Polaris, right?
Yes.
Okay, how does that prove flat Earth?
Well, if that Polaris never shifts positions in there and the stars actually do perfect circles, it proves we're not moving. It proves the stars are moving.
But Polaris does shift position through the ages.
Angel, stop swearing for a second. Stop swearing. So this is the Georgia Guidestones. Here's the hole he's talking about. It's like the thickness of a straw. You look through and Polaris is there. Polaris takes a tiny little circle every year. You can see it take a tiny little circle. Or is it every day? Every day it takes a tiny little circle.
Yeah.
Right. So they tell us that we're so far away from Polaris, 433 light years. Again, we can still see it. Impossible.
It seems weird, yeah.
That our 4.4 billion miles a year of lateral motion chasing the sun over thousands of years doesn't change, right? But because it's so far away, there's no parallax. Again, that's crazy. But the Earth also wobbles, and it wobbles 1 degree every 76 years. Okay, it's got a 26,000 year cycle. 1 degree in the sky is equivalent to 3 full moons side by side. That's 1 degree is 3 full moons. Georgia Guidestones were built in 1981. They were up for over 40 years, right? It would have wobbled over a half a degree. The Polaris would have been far outside of that hole. It would have been far outside that hole. So we started making videos about it. They started going viral, and then bam. Georgia Guidestones exploded, blew up. Terrorists blew them up. 3 hours later, the bulldozers were there. They took it all away and stole the time capsule, and no investigation.
Get rid of the evidence, eh? Well, okay, but when were the Guidestones built?
1981.
Okay, so 81, what is that, 24, 50, almost 50 years, whatever.
And Polaris was still right in the center of that hole.
Yeah, but probably in another 200 years, you would be looking through them and you wouldn't see Polaris. Like, don't you think?
Wait. So you're just speculating.
I am speculating. Yes, I am.
They have, but they didn't move in 40 years, but in 200, they're going to move.
Well, I don't know. I'm just saying Polaris, in theory, should not over time be in the exact.
In the globe religion theory.
Religion.
It's a religion because there's no proof.
By the way, the star trails are making perfect clean-cut circles. They don't intersect each other. If you're spiraling through the galaxy, the star should be a spaghetti ball in the air.
Yeah, the reason this all works is because the distances are so far away, right?
So far away. We're traveling 4.5 billion miles a year. They tell us that that 80% of the stars in our galaxy are binary. So they're doing like this. Some of them are trinary, which is insane, right? We're all moving in all different directions. But all in history, no two stars have ever crossed due to parallax. It never happened. It's never happened, right? This is Coral Castle. You're familiar with Coral Castle, right? Coral Castle is this guy, Edward Lee Scallon, built it himself. He's like 90 pounds, used no heavy equipment. Crazy. But this hole right here has a little X in it. And when you line up, there's a hole in this little triangle across the way. And it shows you where Polaris is, and Polaris actually making a small circle. It goes whatever quadrant it's in will tell you, and it actually just goes here. This is winter, spring, summer, fall, whatever, and so it makes this little circle here. We're wobbling. This has been up for a long time, and it's still there, right? My prediction is this thing gets knocked down by accident somehow. Okay. But again, these monuments prove that we're not wobbling, right? Because the parallax, a wobble doesn't matter how far something is. A wobble will take something right out of line.
So your position is the same as when you started, that the Earth is a fixed, non-rotating, flat plane of some type. The Earth, that's what the Earth is. The sun and the moon are not as big and not as far away as they are. And then I believe you said that you also believe that there is a barrier between the atmosphere of the Earth and the vacuum of space, if the vacuum of space exists. All right, fair enough. So how do we explain, okay, so the moon landings, for the sake of argument, let's just say they were faked. Fine. Let's put that aside. The lander does look a little poorly constructed, but let's put that aside. What about all these missions to Mars, like Elon Musk? What about all these rockets he's sending up, all these satellites? And we're going to land on Mars in another year or 2 or 5. Like, it's getting close. So
they've been saying that since I was 10.
Oh, I know. Trust me. I remember landing on Mars in 1990. It's come and gone. It's never happened. But okay, but eventually, somebody is going to call somebody on this.
Okay. Eventually they're going to break the second law of thermodynamics and go into space that doesn't exist.
But if there's a barrier, how do they smash? Like, okay, listen, hang on. Let's backtrack here.
Correct. You're right. They're not going to do it.
All right, wait. Where are these rockets? Okay, where are Elon's rockets going?
All right, let me show you.
Bermuda Triangle? Like, where are they going?
Let me show you.
Where's the golf ball go?
I don't know. Back into the ground.
Matthew, follow this. This is one of Elon's rockets that he's testing. It's going to go to Mars. It's just to give you a scale for size. You can drive.
Is that the Starship?
This is the Starship. You could drive a Mack truck underneath here. Okay,
that's big,
right? Okay, watch this. Now think about this is tens of tons. Okay, right? So,
oh God, more than that.
Yeah. So watch. This little flame is going to come out of here, and then. Look at the thrust. Now watch this thing. And of course, edit. Now I did cut out some sections here, but look at this. This little flame is pushing this thing up where all of that smoke would be obliterated. But look at it. Edit. We got a side view. We still have a side view, so it's not up that high. Now watch the engines here. Now we have a rocket view. Now look how fast it's moving. Look at the smoke. It's not moving very fast. Now we have hold on. Just follow me. It's going to go quick. So now, the engines have turned off. It's falling. Now we have a side view still. How high is it? Look how slow it's moving. Now watch when they edit the speed of the smoke. Ready? Is this free falling? This is tens of tons free falling.
No, that's...
Okay, no, but then hold on. This is Elon Musk. Whoa, look how high it is now. This is not out of order. This is off of their live stream. Now watch. These engines are going to turn on. It's magically going to go upright and, oh, look how high it is all of a sudden. Right? And then it's going to... Two of the engines are going to burn out. Ready? It's going to click on. Cameraman's going to get right underneath it. 1, 2, 3 engines. Cameraman gets underneath it. 2 of the engines are going to burn out. Ready? 1, 2. And it's going to land upright with a whole bunch of CGI smoke. Okay? Look at that CGI smoke. And it's going to land. Do you believe that is real?
It looks fake. I get it, but
okay, it's fake because it is fake.
One of the things. Wait a minute. Are they using some? Okay, listen, guys. Okay, yeah, it looks fake. Are they using a new type of fuel? Because I remember when the space shuttles were shot up, like that was a smoke show from hell. And
that's
when
right.
The Saturn V went up, like, I mean, why are those flames? Are they using a different type of jet fuel? Because that thing's burning pretty clean.
Matthew, can I get in here for a second?
Yeah.
So Newton's third law states,
action reaction.
Object A has to exert a force on object B to create an equal and opposite force. Object A will push off. Okay. We put a drone in a vacuum chamber. We don't suck out the air. The drone can fly in the vacuum chamber. We suck out the air. It can't fly anymore. Correct?
Yeah, for a drone, because the propellers, they require a Yes.
Okay.
It will not fly in a vacuum.
Ionic propulsion, I can show you a video of ionic propulsion, which NASA claims to use, not working in a vacuum because there's nothing to push off. If I'm on a skateboard and I push off a wall, I push off a wall on the skateboard. My arms are object A. I'm attached to the skateboard, and the wall is object B, and I'm pushing off it. Now, if I start doing this on the skateboard, I'll push the back of my head. I'm not going to move anywhere, correct?
Yeah.
Okay, what's the rocket pushing off in a vacuum?
What's it steering with?
The burning of the fuel. Well, the burning of what's happening is the burning of the fuel. Let's just say the explosion from the fuel. It's going in every direction, but in the direction downwards, there's nothing there. So the thrust doesn't actually push down. The thrust actually pushes up. So in the combustion chamber, the explosion goes in every direction, but the only direction that has something to push back on it is above it. So what happens is the thrust pushes up, and then the rocket pushes back. So that would be how. Okay. Yeah, that's basic third.
It's pushing. It's pushing off itself.
Correct. Yeah, but this is like if you were on a skateboard, like if you were sitting, or even in one of those chairs like I'm sitting on now that have wheels, and you held a bowling ball, and you threw the bowling ball would go in one direction, you would go in the other because you're pushing off the inertia of the ball.
Let me get here. Exactly. So the mass of the ball is now object B. In a vacuum, there's still no object B.
No. That would work what I just illustrated there with the ball, the bowling ball, and the wheel, the chair with wheels would work in a vacuum or out.
Yes. I agree. I agree. So in a vacuum, these rockets would literally have to expel almost all of their fuel just to move a little bit.
The vacuum situation is interesting because the vacuum would pull the thrust out, kind of like a vacuum cleaner, and
Exactly.
it may be easier to pull it out than it is for the combustion to press up on the rocket engine.
You have two problems. The one, you can't have combustion in a vacuum.
Well, they bring their own oxygen.
In a vacuum chamber, we have rockets that don't move. They literally.
Wait a minute. Well, who's tested that? Be careful with that. Like, honestly,
we have videos.
I can show you.
Okay, but be careful. How big was this vacuum chamber? Because if it's a small vacuum chamber like this, there is a possibility.
That's a problem for us. A small vacuum chamber lets that expulsion actually build a little pressure and will move. It still doesn't move.
Yes, but
the bigger the vacuum, the better.
If you're using a massive one,
that's better for us. It's easier to prove our point. Yeah.
Well, why don't you run an experiment? Some universities have those large vacuum chambers.
We've done it.
Really?
It's already been done. It doesn't work. It violates Newton's third law.
Can I show you? You meant
I would love to see that video. If you're telling me that Newton's third law does not apply to a rocket engine in a vacuum, then you're going to set the world on fire. But it's got to be a controlled experiment, because if you mess around and you do something wrong.
All right, Matthew, you mentioned the space shuttle. Did you want to show something, Angel, before I do this?
No, you go ahead. I'll get it up there.
So here's the space shuttle. The space shuttle. Remember, we love the space shuttle, and it left those giant plumes. Now look at this fence right here. Think about a hurricane. A hurricane will pull trees out of the ground at 200 mile an hour winds. 300 mile an hour, 350 mile an hour tornado will pull foundations out of the ground.
Yeah, I can imagine.
Okay, so the thrust coming out of this thing is 17,500 miles an hour minimum. It's actually faster than that, and it's superheated.
So that's the velocity, the
velocity of the thrust. This fence doesn't move. Now watch right here. It's going to go up, and then it's going to come back down. 4 million pounds up, and then back down. Right? It did a little bobble. Right? Where this thrust should send these clouds for miles. Right? But this thing is just going up. Now, it goes up in space. Now, I don't have the sound on this, and you can just look Space Shuttle launch. You'll get this. When the solid rocket boosters deploy, they're 35 miles downstream, and you hear it at the exact same time that you see it. You hear it at the exact same time you see it in the video.
No, you can't. That can't be.
Well, but in the video, just look, Space Shuttle launch, you'll find this video. And right here, when it goes, you hear it and see it at the exact same time. It should be over 90-second delay, if you could even hear it from that distance. Right? These things are gonna go off in 2 seconds.
Speed of sound versus the speed of light.
So right there, that poof, you heard it at the same time in the video. So you can say, oh, they just did it for effect. Okay, you can make
maybe they edited it.
Okay, yeah, maybe they edited it, but that was live. That was live. Now check this out. This thing, empty, is falling back to Earth, and it's supposedly going to deatomize. You know what this window is?
What do you mean deatomize? You mean atomize?
Atomize. It's supposed to burn up before it hits the ground.
It's like defrosting.
Yeah. So check this out. The guys filming it are on the shuttle heading upwards at over 17,000 miles an hour. This thing is free falling to the ground, and they're keeping it in frame for minutes. How is that possible?
I don't know.
Oh, wait, I don't know. Right. So see this picture of the Earth here, right?
Yeah, it looks like the Earth. Yeah.
It looks pretty cool. You can almost see the curvature, right?
Well, the lenses cause like the use. Yeah. I mean,
yeah, but don't get mad at me. We filmed this. in our front yard, and we just got a solar panel. I'm just showing you with no budget how easy it is to.
You pulled the wool over my eyes. You had me going. Is that your tank or is that your barbecue tank?
So this is actual footage of them. Now, does this look like it's free falling? Now, watch this. We filmed this. Tell me what you see here. Ready? On the right side, right over here. Ready? 3, 2, 1. Right here. What is that?
I don't know. That was weird.
So I'm going to make it slower, right? What it looks like some sort of quadcopter cloaked in some way, like a blimp recovery, right? I'm going to flip it.
Okay. So Romulan.
I flipped it sideways.
Device,
Again, this is a balloon recovery.
yeah.
NASA uses more helium than the rest of the world combined times 1,000. They control 99% of the helium in the world.
What are they using it for?
They're blimp rockets.
We have to start to
round it up.
in.
Yeah.
Yes. Right now, which I mean, this is fascinating because I've never ever seen anything like this.
Yeah.
Yeah.
So
hey, what was that? What is that?
that we don't know. We don't know what it is.
That looks almost like a drone.
Thank you. It's some sort of a craft.
Did you guys?
This is legit.
Footage?
This is from their live footage.
Maybe this is how Elon Musk. How does Elon Musk get pictures under the rocket? Like, is there a drone flying around his rockets?
It's all fake. All of it. Nobody goes on those rockets ever. Nobody goes to space. Space does not exist.
Oh my God. What about all my Star Wars and Battlestar Galactica shows? I'll never be able to watch them the same.
No, you can't. And unfortunately, that's the hardest thing. You can still like them, though. They're still fun.
Well, it is science fiction, so it is fiction.
Yes.
Yeah.
Angel, definitely go ahead and show what you want to do. We'll leave that as a last clip at least before we get closing.
Yeah. This is. What is this?
Okay, so this is ionic propulsion. Okay, so it's got a little spindle and it's got two crafts that are basically pushing off the air. Okay, now he puts this basically in a vacuum chamber, and it has air in it now. So what he's going to do is he's going to suck all the air out. You can see on the gauge there, the air's going lower and lower, and when it reaches a vacuum, a really good vacuum in there, it starts to stop. It doesn't have any air to push off anymore. And you can see it eventually completely stops. It's just running off the motion it had now, and then it will eventually completely stop.
What's the mechanism of propulsion you said?
Ionic propulsion.
So what is it doing? It's shooting electrons out of the
shooting ions out. Ions, yeah.
Well, ions are okay. All right, yeah.
So now what he's going to do is he's going to reintroduce air into the tank, and then it's going to start up again. It's going to start pushing off the air again, right? So now you can clearly see it doesn't have any air to push off, and it's completely stopped. So this debunks, even if we grant you the vacuum, space travel is fake. It can't happen. It's impossible. You can't push off nothing. So I'm just going to speed it up to where he puts, there you go. He introduces air.
So Newton's third law. This is kind of contrary to that.
Exactly. You can't push off yourself. If you're on a skateboard, you can't push your chest to move. You need to push off something.
Well, that's fascinating, actually. That's it's a good experiment for a physics lab. But you need a very large vacuum chamber, and then maybe just like a small rocket. But it doesn't even have to be a rocket. It could just be a compressed air cylinder. It would
exactly
work.
It's been done.
Yeah, really. I'll YouTube that. That's actually quite fascinating.
I have to give you a warning. With all the information that we gave you today, if you actually look into this, you're going to end up rejecting the globe. Okay, I don't want to call you a flat earther. You could be a true earther. You could be a level plane earther. You could be a realm earther. You could be an extended plane earther. You could be a domer.
Look. This is the way I look at it.
The globe is dead. It's over.
Okay, a lizard in a terrarium. How aware is he of his environment, the light in the sky, the food that's given to him, the water. He has no awareness. He can only understand things to the ability that his little reptilian brain has, right? Now, we as human beings have to recognize that, as much as we think of ourselves, we may not be the sharpest tools in the shed, and we may not have a perfect understanding of reality. Now, your reality is a little bit outside of, and admittedly, it's a little bit outside the mainstream of, Newtonian mechanics and relativity and physics and all that. We have a whole model of our world based on those equations, those realities. However, science, contrary to what other people may think, is about investigating and testing other things. And there's a lot of crazy theories in the world that we're crazy, that are not so crazy. And you know what they say these days, the only difference between a conspiracy and the truth is 6 months, right? So it's always good to apply the rules of physics, because look, guys, the rules of physics actually do apply. Like, I can calculate if, the trajectory of an arrow or a football, they do work. And you have to admit that most of the laws of basic Newtonian mechanics do work. Like, we can calculate things. Now, there is a lot of ambiguity and obscurity regarding perhaps gravity, your understanding of gravity. I know that there has to be a force pulling it down. We call it gravity. I mean, is it possible that it's something else that we don't understand? Sure. Who knows? But,
or that we do understand, electrostatics.
Again, I'm not an electrical engineer, but yes, we know that electrostatics can cause effects similar to gravity. We know this. It's not even controversial, and it's, nobody will say it's controversial. So
it's scientifically provable. Gravity is not. Gravity is a religion.
The religion of the G, right? The big G.
Exactly. Which, the same reason a helium balloon floats, it's less dense than air. A rock is more dense than air.
Dave, you've got the round table up there. I know that has to do with the why.
I'm going to make this super tight because we're way over. Why. Okay, so let me finish. I'm going to make a short rant. It's not going to be too long.
Yeah.
Right? So the Council of Foreign Relations, the United Nations, the Bilderberg Group, the Club of Rome, the Royal Institute of International Affairs, and the Trilateral Commission, those are the people that we know. Who are their rulers? Okay? Where do they get their information from? I think their rulers are in lands where we're not allowed to go, lands beyond Antarctica, maybe who knows where they're going from, right? So how do you piss off a baby? You take its ball away, right? Not much difference between a grown man, because your entire world is based around this. Now, what they don't want us to understand is that we are these incredible, powerful beings. We're in this realm. We're part of this living system. The moon controls women's menstrual cycles. The sun controls men's cycles. Where the sun and the sun and the moon, the sun is electric and the earth is magnetic, and we are electromagnetic. We live in this incredible realm at the center of creation. This place was created for us. It is filled with abundance, and it is magical if you don't understand what this place is. Our thoughts create our reality. Look at your life. It's your fault. Everything that you think, you attract. Your thoughts are magnetic, right? They don't want you to know that. Yep. So what they do is they literally put a globe over your head and they say, this is where you live, a world of limited lack and fear. Okay. It's a prison for your mind. And when you're in that prison, you don't even see the bars. Right? Because you're lost in there. So why would they, what has Flat Earth done for me? Well, I'm more at peace, greater sense of freedom, closer connection to the creator, no fear whatsoever, right? Fear is the only way that they get you. So divine law is the law of God. Common law is the law of the land. Statute law or admiral maritime law is the law of the sea, or man's law. And this is important. In order to convince man to give up his divine rights and their common rights, you have to convince them that they're not divinely created in a divine world. And that's what they do. The globe lie is the one that's hiding everything from us. They're hiding free energy. They're hiding the creator. They're hiding our spirituality. They're hiding more land, more technology, more resources, right? Scientific knowledge, excuse me. They're hiding that we're special, that we're at the center of creation, right? So How can everyone be in on it? They're not. You're not in on it. And for all of your life, you've been defending it. Until today, you're now thinking. You're now looking at some stuff that you may never have thought of. They've literally made the prisoners the wardens of our prison. And once you can break that freedom, once you can break that, you literally unplug from their matrix. You unplug from their reality, which is not real. Like, and if you live in fear, false evidence appearing real, FEAR, and you listen to the news, north, east, west, south, to steer your mind, you are lost inside of their system. And, again, if they have you on their globe, right, you have to play by their ball field rules. You have them playing with their fake money, right? They control you with money and fear. That's how they control you. When you understand that we're at the center, that there is no G warming, and I don't want to say it because I don't want YouTube to flag it or anything, that there's unlimited resources, that there's no overpopulation. The population of the earth is well under 3 billion, I think. Really? Okay. Well under. Right. And there's statistics. When you see these statistics, you're like, wow, I never even thought about that, because they're literally keeping you in fear. Right. They want you to believe that we're overpopulated. You could take every family in the world and give them a quarter acre in Texas, and then the rest of the world will be empty. OK, it's absolutely ridiculous. And that's with 8 billion. OK, yeah. There's no way that there's 8 billion people. Right. There's no possible way. They want us living in fear. Angel, what do you want to add to that?
What they've done is they've hidden the creator who created heaven and earth, and they've basically assumed the role of the creator by doing that. So now who do you worship? The GOV. Okay. So you think you have to get up and work all your life and then retire at 80. No, we should be in utopia if everyone knew the truth, because we could have free energy. We could have unlimited resources. We would know that there are no outside threats, no aliens, no
asteroids,
no meteors coming in to kill us in any second. Right? It's
interesting. So let me get this. Well, let's do a little thought experiment. So if all of a sudden tomorrow on CNN or BBC they announced that the Earth was flat and limitless, or at least, flat, there was a protective dome above the Earth, that would be the end of atheism, wouldn't it?
Yes, it would.
Yes. They would ask you, the atheists would be like, okay, well, hang on a second.
I was an atheist before I discovered this.
Who made the enclosure we're in?
No. Even. Yeah. I look. Trust me, if there's a physical structure and the Earth is a flat plane and there's no stars and planets, the church would be in charge, not the state.
It's gone.
No, actually, the church might not even be in charge anymore because they were in on it as well, right? Interesting. So you think this is a psyop? This is a psychological operation?
It's basically just to hide the truth and the creator and free energy and resources and everything.
Well, you know what? In all fairness, that would be pretty cool if that all existed and the Earth was.
Matthew, let him finish his point.
So they're hiding that from you. So if atheists knew that suddenly we are contained like a giant terrarium, they would ask, well, who made that terrarium? Who built that structure in the sky that's containing our gas pressure? The answer to that question is on page 1 of the Bible.
In the beginning,
God separated the waters from the waters and created the firmament.
Yeah, in the book of Genesis, in some of them, they actually even draw the firmament in there. I've seen it in some.
Yes.
Yeah.
Yes.
So it shows the firmament, it shows the stars and the moon and the sky and the sun inside the firmament. Yeah. You see it, actually. Yep. I don't have a Bible kicking around. It's probably in my library somewhere, but...
I could show you depictions if you want, but they used to be.
Yeah, no, I know the depictions. Actually, Will, you have a sort of depiction of that as your logo for your channel, don't you?
I do, but, funny enough, the inspiration for that came from Gnosticism, actually, in a belief that you obviously, well... I guess it shares some sort of relation to...
No, you have a little guy peeking his head through the firmament looking on the other side.
Absolutely, absolutely. But I'm saying that the inspiration.
That's why I accepted your request, by the way, for an interview. I saw that. I'm like, all right, this guy, he doesn't know it, but he gets it. Yeah, he's secretly a flat earther.
Without knowing, it's somewhere in my subconscious, right? Right there, it could be.
Yes.
You've always known. You've always known.
Yeah.
Well, this is interesting. Like, there's obviously some things that I have to. I mean, that's it. Yeah, that's it. I've seen that before. Yeah, the world of the Hebrews. Wow, maybe they had it right, eh?
That's what we live on. Yeah, that's what I believe we live on.
Well, guys, I hate to break it to you. I hate to cut this off for you, but I've got to also make sure that my editors will have a chance to do this. They're going to try and get this out on Friday, and so we kind of have to kill it.
Let me just wrap up. Look, this is my app. I have an app that teaches you about flat Earth because Google doesn't want you to learn. These are people that have my app, which represent less than 1% of the flat earthers out there. They're everywhere, but on the app, very important is if I click this button right here, which is the more resources button, and this is what I want you to look at is right here, experiments. This one right here, we've done all of the experiments for you. We've documented all of them. There's also the frequently asked questions. Every question you could ask, why to lie? Amazing videos there. Eclipses, where does the sun go? There's even a homeschool section. There's books, tons of books, right? Biblical books, novels, old world books, kids books, all sorts of stuff. And there's amazing stuff in this section. This is the homeschool section. And I just added this girl. You got to check her out. We Are All Energy. She talks to AI, and she's got her AI is reflecting her consciousness. And it's amazing. It's absolutely amazing. I literally just added this yesterday. But
what's the app called there, Dave?
It's called the Flat Earth Sun, Moon, and Zodiac Clock. All you have to remember is flatearthdave.com. Just go there and click the banner. Click the banner.
Yeah.
And it has everything. It has a biblical section. Amazing stuff here. Really good stuff. You'll love this girl, Kay Podge. Amazing. All biblical stuff and mind-blowing stuff.
You know, some of the stuff you showed me is interesting. Like, look, I'm approaching everything from a math and physics perspective. So some of the things you showed me, the numbers didn't quite add up, like in terms of the platform and the curvature and things like that, the refraction and, you know.
Didn't add up for the globe.
Yeah, sorry. It didn't add up for the globe. Like, I'm assuming all those numbers are right. Those pictures are true. So I'm not going to even, I'm not calling anybody a liar. I'm going to assume those are correct.
What happens when you verify that we're right and they're impossible? What happens then?
Look, it's important to always have a rigorous scientific process to review these things. If indeed those things are as you presented them, and they do appear to be, then it does raise some questions regarding, other things. Perhaps is refraction. Look, we've been at it for 2.5 hours. We could go for at least another 2.5 hours because I haven't even scratched the surface. I haven't even pulled out equations to see what you guys take on that. But it's all very interesting. I did like some of the NASA shots. They did look fake, but it's NASA. It could be just who knows what they're doing with all that money. It's it's a government organization, right? But so who knows? Whatever. But yeah, it was really interesting, guys. I really enjoyed the conversation. Again, I didn't want it to be confrontational. It was enlightening. I saw some things that piqued my interest, and next maybe I will run an experiment between two tall buildings. I just don't have the GPS equipment. But maybe, we could do a video of an expedition. All four of us will go out. We'll do some calculations. Maybe get out on a lake and see if we could see further than we can.
I think there's always got to be an evolution.
I know that I could see further than I should because I've been out on lakes before. I always attributed it to refraction, but now that I think about it,
refraction, magical refraction, or flat Earth, simple.
It's just flat.
Like, your explanation would be the easiest because then I don't need math. I can just use my own senses, right?
The Navy railgun can shoot targets well over 100 miles away. At 100 miles away, there's 6,600 feet of a hump between them. Makes no sense. They could laser them with a target them with a laser, and then line drive.
Well, even radio doesn't.
Radar.
Right.
A radio shouldn't work over the horizon either.
Microwaves go 10,000 miles when they shouldn't go 80 miles.
Yeah, Marconi, he get his transmission.
Hey, how did Marconi do that across the ocean?
Because the Earth is flat.
Yeah, because no, I'll tell you how it worked. Because he shot it into the sky, he bounced it off the ionosphere that he didn't know existed.
Marconi, I forgot about him. Yeah, he sent radio waves across the. You can't do that. Interesting. I'm no telecommunications engineer, but that does seem like a long way.
That's why they say the ionosphere exists now.
Oh, they made it up for that?
That's why.
You guys are awesome. I really enjoyed this. Like, maybe we could do it again sometimes, eh?
Absolutely.
Like, you know what? Well, we got to have some kind of conference on this.
Yeah. There's going to have to be an evolution of this. We'll put our minds together here. I definitely, obviously, I appreciate you guys taking the time to do it.
I think we need to do an experiment and
Well, why don't you go to that experiments page on the app?
I will. I'll check it out. Dave.
Most of those experiments have been done. We've done mirror flashes, lasers, balloons. We've done everything. And they're all, every time it comes out, flat Earth, no curve.
Hey, what about the retro reflectors on the moon? Like, doesn't that prove that we landed on the moon?
They were bouncing stuff off the moon before that.
Yeah, that's how they figured out how far the moon was.
Okay, okay. Wait, I forgot to. Yeah, retro reflectors. Yeah, they bounce lasers off. It should take 2.5 seconds to get back.
So check this out. They send out 100 quadrillion photons, and then one comes back, and a computer run by NASA goes, "Bing."
Yeah, but you can trust them.
Yeah, thank you. There you go. We can trust them.
They're a government agency, aren't they?
Yeah.
Hey, Matthew, NASA is the only part of government that doesn't lie. Don't worry about it.
No, I'm. Well, guys, it was a pleasure. Will, this was awesome. You cobbled together two upstanding gentlemen here for a good discussion. I like that.
Definitely. I think it'll go well. I have no doubt there'll be plenty of questions. I mean, we didn't touch even half of the questions that I continue to have. So we will do this at some other point. We'll bring some evolution to it because I think it's cool.
Yeah, we should talk more about, look, we can do more experiments, but I think we need to get deeper into the philosophical aspect of this.
Next time we book it, pick an earlier time than 10 a.m. Eastern. Earlier the better, because look at poor Angel. He's right over here. What time is it? Like 3 o'clock in the morning?
Yeah, 2:40. 2:40.
We didn't even discuss time zones. We got to figure out these time zones.
Time zones.
And why are the time zones in the north different from the time zones in the south?
Because the south is bigger.
Because it goes around.
Yeah. It's 3 o'clock in the morning where he is. And right here, it's just after noon for me because I'm right here. And so are you. You're right along this line. Yeah. And so when the sun's his sun's going to be rising soon. You better get some sleep, Angel.
Oh, now those flight paths make sense. Flying from.
Yes.
Oh wow.
Yes. Can we look?
Yeah. When you look down, it makes sense why you fly to Dubai to get to Johannesburg.
Yes. Can we just look at one type? I know Will's going to kill me. Look, New Zealand to Argentina. Ready? New Zealand to Argentina. It goes all the way up to San Francisco, Texas, and Argentina. Look at it on a flat Earth map. It's a straight line.
You're blowing my mind here.
Thanks, Will.
Yeah, that makes perfect sense. Okay, listen, guys. I am not endorsing anything you said. All I'm saying is that is interesting. That is interesting.
I'll take it.
We'll take this to part 2 or whatever part, because we haven't even touched upon this, because there's a lot of emergency landings they do. I'm wondering where they land emergency-wise.
Oh, I have them all listed, but we don't have time. We don't have time.
No. I don't want to get into it. We'll do it next time. All right, guys.
All right. Appreciate it, guys. We'll see you later. Everything is linked down below.
See you. Thanks.
Take care.